Okay, so welcome back to our last series of seminars for this season here at BrIAS with our BrIAS fellows. Today we have a kind of slightly longer program than usual because we will have our usual seminars. Then we have a third seminar instead of usual two with a special guest. And we will also have the closing ceremony for this season of BrIAS with various people who will intervene. It is really my pleasure, and I'm very happy to introduce the next speakers. In particular, I have a very special debt of gratitude with the first two speakers because I've been some of the most important people in my career. I will start with the first, that is Professor Ilya Kolmanovsky from the University of Michigan. So he's a dear friend of our university. This is the third time that he stays here on a long stay. The first one was something like 8 years ago with a chair in from ULB. And then 2 years ago, he was awarded the chair Jomot at the Royal Academy of Sciences, and we organized several events there. And now it's here as a BrIAS fellow. Now, Ilya is one of the most known researchers in our area. He has a long list of prizes, which I will not mention because it's really long. And I see that he's happy that I don't mention it. And he has a very peculiar career because after his PhD, rather than continuing in academia, went for a long time in the industry. So he was for almost 15 years in Ford Motor. While being in Ford Motor, he was keeping doing both applied and theoretical research of a very high level, and then he came back to the university where he continued this amazing career. So he is author of various hundreds of papers, author of more than 100 patents. I think you crossed the 100, Ilya. You crossed the 100 patents. And is really very well known in our society. Is also the editor-in-chief of the IEEE Transaction and Control System Technology. And most of all, is a very dear friend, and he has always a lot of very interesting things to say. So I'm very happy to give him the podium.
Thank you very much for a very kind introduction, and I'd like to thank BrIAS for for giving me the opportunity to spend time here in Brussels, interact with colleagues and Professor Garoni and other colleagues visiting BrIAS. Was really wonderful time and very productive time with a lot of good ideas and good exchanges. I'd like to say a few words about some of my research and some of the adventures in an area called model predictive control and computations. Before I do that, I just want to tell you a little bit about my broad area of research, and that involves control of systems with constraints. And in automatic control, you typically have a system, we call it plant, that you're trying to control, and then you have a controller. And then in the traditional control, what you'd like to do is to cause certain outputs of your system, here they're denoted by Z of t, to track certain references, which are denoted by R of t here. And what makes constrained control unique, or what distinguishes constrained control, is that you have additional requirements on this or other variables of the system that they have to belong to prescribed ranges given by the set capital Y. And examples of constraints include things like safety limits, obstacle avoidance requirements, comfort limits, actuator range and rate limits, as well as constraints can be more interesting. They can depend on time in case of moving obstacles, or can be given by temporal logic expressions. And why do we worry about constraints is because bad things can happen if constraints are violated. Cars, ships can roll over. The aircraft engine can catch fire because of compressor surge. Battery can overheat. Aircraft can disintegrate in flight due to excessive loads caused by maneuvers and gust. And actuator or control surface rate limiting can induce pilot-induced oscillations that can cause aircraft crashes. And that's what we would like to avoid. If you take a flight, it's interesting that one of system with many constraints is the aircraft gas turbine engines. There is surge margin limits, overspeed over temperature limits, combustion limits of various kind, actuator range and rate limits. And as aircraft is becoming more electric, you have to also worry about constraints in electrical power system on currents, voltage, state of charge, and so on and so forth. One of the most appealing tools developed in control theory for addressing constraint control problems is what's called model predictive control. And in model predictive control, you generate control by solving a discrete time optimal control problem. So the feedback control law is obtained through the optimization. And the optimal control problem, the constrained optimal control problem, might look something like shown here on a slide. And here, let me make sure that I have a pointer. Here you have a cost function that you're trying to minimize that reflects your performance objectives. You have certain variable, you have state variables, you have a model, which is used as a constraint. And here, whenever we have a hat, that means the predicted state and predicted control. And then the way you enforce the constraints is by imposing those constraints as a part of this optimization problem formulation. And so the first element of this optimal control sequence that solves this optimization problem is assigned as your control action. So a couple of remarks here. Typically, you use iterative optimization solvers to find the solution. And so you have to solve this problem in real time, and that's why computations are important. And so the control law is not given by explicit expression like a PID law, but it's what we call algorithmically defined. You can obtain it after executing a particular algorithm. Often people refer to a diagram that I show here on the right that illustrates the prediction performed at time k. You predict the trajectory forward in time, you optimize this trajectory, you apply the first element of the optimal control sequence, and then what happens is that the real system doesn't behave like your model predicts. And so what do? Well, you repeat this process at the next time instant, and that generates a form of feedback to compensate for the uncertainty. Model predictive control has a long history. It emerged in late 60s in academia and in late 70s in industry, basically independently. It has been a vibrant discipline for academic research for several decades now. And it has been very successful in chemical process industry, and there has been increasing interest and adoption by other industries, notably automotive industry most recently, and I showed a few examples where it was actually introduced into mass production. Now, this is my introduction, and what do I want to do for this talk? First, I'd like to tell you a little bit about a few applications where we use model predictive control. Applications are always fun and gives you a little bit more idea about some of the applied research that I do. And then the Achilles heel of model predictive control is in the computations, because you have to solve an optimization problem on board, and that's difficult. And in fact, that's a major motivation for looking at alternative schemes, such as reference governors, this major area of research of Professor Garonia, as well as barrier functions and control barrier functions that have become popular recently. Hopefully, by the end of this talk, I'll convince you that there are a number of approaches to generate lightweight implementations of MPC that simplify the computations greatly. And so then you can take advantage of the fact that MPC is a very versatile framework that reflects performance objectives, handles constraints, and can have a low computation effort. If I have time at the end, and I'm not sure that I will tell you a little bit about how we can take ideas in computations and model predictive control and apply them more broadly to study the optimization algorithms in multidisciplinary design optimization. So there's more an area of design or area what's called control co-design, where you worry both about design and control together. So let me start talking about applications. And as I said, that in MPC, an optimal control problem has to be solved on board. And so the deployment of MPC still represents a very significant challenge, in particular in small aerial platforms like quadcopters, where onboard computing power is quite limiting. And here we are testing MPC controller for elliptical trajectory tracking in our M-Air facility at the University of Michigan. But MPC solutions based on onboard optimization we are able to realistically implement are limited due to the lack of computing power. Here is even a more significant challenge, both from computational control standpoint, which involves control of aircraft with high aspect ratio flexible wings. Such aircraft are of great interest as high aspect ratio wings increase lift to drag ratio, and therefore they can improve fuel or energy consumption. You can also use them as high altitude, long endurance platforms, basically pseudo satellites. Unfortunately, these aircraft are also very flexible, and they can experience high deflections and loads as they are exposed to maneuvers and wind gas disturbances. Furthermore, they have fairly complex dynamics, as you can see from these videos, and the models for them are high order, maybe between 100 and 1,000 states. And they also have numerous structural and control effector constraints throughout the aircraft structure that you have to worry about. So some of the work on the computations has really been motivated by looking at applications of this kind. MPC can also be used in spacecraft control applications, in particular for station keeping and rendezvous and proximity operations, notably on halo orbits in cislunar space between Earth and the Moon. And here, to enable low fuel consumption during station keeping, there needs to be special formulations of model predictive control used, and that requires accurate models, nonlinear models, and non-standard choice of cost functions. And of course, these non-standard problems, optimization problems, need to be solved reliably on board of the spacecraft. We have considering the use of MPC to handle constraints in deep space applications, for example, for soft landing on asteroids, satisfying various constraints. Then if one wants to improve the ability to fly around and land on an asteroid, essentially without much knowledge of the gravitational field, MPC and adaptive control can be integrated together. And I wanted to mention these developments because they happened under an AI planning grant from the National Science Foundation that Professor Bruno Sinopoli, who is the next speaker, has led. And this work was in collaboration with Professor Spenzau and Naira Havakimen. Here we integrated L1 adaptive control to compensate for gravitational field uncertainty and model predictive controls, as well as reference governors in other articles. Another application for which we successfully exploited MPC involved the reduction in emissions of diesel engines, and they are used to power trucks, ships, and interestingly, even some airplanes. And the controller architecture that evolved was actually quite interesting, and it involved not a single MPC controller, but actually 3 of them, and 2 of them were controlling the air pass of the engine, basically exhaust gas recirculation valve and variable geometry turbocharger. And the 3rd MPC controller was outer loop MPC controller that would adjust the set points to this inner loop MPC controllers, as well as the fueling rate. And while this architecture is quite complex, it enabled us to gain fairly good control over the engine transients, and we've been able to reduce transient oxides of nitrogen spikes, which is a difficult thing to do in diesel engines, and we've been able to do it with this architecture. And what's interesting also that thanks to some of the ideas on the computational side I'm going to talk about, we've been able to maintain the total computation time for all these 3 controllers under 1 millisecond per time step. There have been a number of applications we looked at to hybrid electric vehicles that exploited interesting ideas and interesting cost functions in optimization, including those based on game theory. Broader use of game theory we also considered that in applications to autonomous driving. And here what we worry about is interactions with human-driven vehicles, in particular in scenarios where an autonomous vehicle has to take into account these interactions. If the autonomous vehicle trying to merge into very dense traffic where there is a lot of other cars, it has to nudge its way in. And so you have to have predictive models that somehow going to account for reaction of human drivers. So game theory provides a way of modeling these interactions. And what we typically do is that we don't use a single game theoretic model, but use multiple of them. And based on the history of interactions, few seconds of interactions, we adjust the probability of each of these models being assigned to a particular vehicle. And then we use stochastic model predictive control to actually optimize the trajectory of our autonomous vehicle in such scenarios. More recent work, I'm not going to dwell on it too much, but that included taking into account perception uncertainty. If you have a camera-based system, you rely on a computer vision to drive in traffic. You have to account for uncertainty, for the errors in this perception system. That's a long-standing challenge. Also, perception systems are often based on neural networks. These are typically machine learning based systems. And the other challenge is that you have to take into account let's see if I can click. I don't think the video is playing. That's OK. You have to keep into account what's known as out-of-distribution perception, meaning that you might encounter during regular driving situations which were not present when you trained your perception system. And so we use deep ensemble type techniques to handle out-of-distribution perception. And if this video was playing, you could see that we are basically testing in environment with rain and bad weather, a system that has been trained in sunny weather. And this is in Carla simulation. Now, there was a very nice conference here last week on the batteries. And we've been also looking at battery control problems more from a higher level systems perspective and on aspects that involve thermal management. And thermal dynamics in vehicles tend to be slow. The temperatures don't change very fast. And what it means is that if you want to prevent the exceedance of limit on the temperature, on the battery temperature, and you can have control over cooling system, you have to pre-cool sufficiently far in advance to avoid this constraint violation. So sufficiently far in advance of some kind of load increase or acceleration of the vehicle. So you need long prediction horizon. You need to look long into the future. And there are two issues there. One is that MPC has high computational cost. And the second is that the forecast uncertainty. You need to know what the vehicle speed and what loads are going to be able to predict the thermal loads on the vehicle. And you need to predict, say, the vehicle speed, let's just say 5 to 10 minutes ahead to be successful. Initially, we were skeptical whether we can do this long-term prediction of vehicle speed, but it turns out, and this is based on historical data, that if you combine queuing models for short-term prediction and then neural network and Bayesian network models for longer-term predictions, you can make some good progress on this problem. And then you can develop special variants of model predictive control, what we call a multi-horizon MPC, where you have different phases, and you have a receding horizon phase and a shrinking horizon phase. And the shrinking horizon phase, you can use lower fidelity model, you can use less accurate preview, and that helps reduce the computational cost. And we've done work developing this multi-horizon MPC formulation. All right, now I gave you a few ideas about applications. Computation in all of them is a serious limiting factor in terms of the type of solutions we can deploy. We have to worry about the computations. And so the need to address this Achilles heel of MPC has motivated us to look more systematically into computations and model predictive control. And I'd like to tell you a little bit about some of the research that we've done in this area that broadly categorized in 3 different directions here, 2.1, 2.2, 2.3. And our first set of approaches was to look at developing solvers, computational solvers, specifically tailored for problems, for MPC problems. And they would be faster. They would exploit special features of these problems, take advantage perhaps of warm start. And this is the work that involves many different ideas. It's the work with many collaborators. I could probably give a number of talks on these ideas. I'll just briefly mention 2 of these developments. And one of them is what we call inexact Newton-Kantorovich method for model predictive control. And this goes all the way to the classical Newton's method for solving nonlinear algebraic equations. So I have a smooth equation, f of x is equal to 0, and I want to solve it. How do I do it using Newton's method? Well, you take a guess for the solution, which is x0. You linearize your nonlinear equation, and you solve the resulting linear equation, and that gives you another guess, x1. You repeat this process, and you converge to the root, right? That's classical idea of Newton's method. Now, it turns out there is a Kantorovich version of the Newton's method where you don't relinearize. You just keep iterating with the slope computed at the initial point, or it could even be some approximate slope. It doesn't even have to be computed at the initial point, but the slope stays the same, so you don't have to regenerate the linearization. And furthermore, you could even don't need to solve the linear equations to completion. You could solve the system of linear equations up to some accuracy, and you still get convergent iterations. Now, in a setting of model predictive control, these ideas are quite appealing because often you have a pretty good idea what the solution might be from the previous time step if you use the warm starting. You already computed your solution one step ago, so now you are recomputing it for the changed state, but the state didn't change a lot. So you have a pretty good idea about what the solution would be if you use warm starting. And so few chip iterations of this kind would be very appealing because you could improve the solution just enough to give you a good control performance and satisfy constraints. Now, there is a challenge, is that in model predictive control, it's a constraint optimization problem. So you don't have a smooth nonlinear equation. You have Karush-Kuntaka conditions for optimality or Lagrange multiplier rule from calculus that you have to satisfy. And it turns out that that is what's known as variational inequality. And one of the things that we have done was to extend these ideas of inexact Newton-Kantorovich method to the case of variational inequalities, derive convergence guarantees as well as the estimate of the region of attraction. And indeed, if you apply this Kantorovich ideas in model predictive control, you could integrate them into sequential quadratic programming or into non-smooth Newton's method as well. You see a nice reduction in terms of the average runtime and maximum runtime. And in this particular case, we use it for spacecraft attitude control with the control constraints. Now, the other development that I wanted to mention along this first line of research is a joint work with Professor Bruno Sinopoli, who is the next speaker. And here we look at continuous time primal dual flow algorithms. And a nice feature of them is that they guarantee the feasibility with respect to constraints. So you have always constrained admissible solutions, irrespective for when these algorithms are interrupted or terminated. So if you are in a situation where your time to compute the solution varies, you'd like to have an algorithm that's anytime feasible. You can stop it at any time, and the solution that you have satisfies the constraints. And then adding a few bells and whistles to this idea, you could also ensure that this solution can be stabilizing and ensure closed loop stability as well. Okay, now let me talk about the second line of attack at computations in model predictive control. And that's where we said that suppose we are not able to solve our optimization problem to completion. Perhaps we are only able to perform a fixed number of iterations per time step. What happens? Could it be that maybe one iteration per time step is good enough and gives us good quality of the solution. Let's say that we are looking at a situation where we have fixed number of iterations per time step, and we also use warm starting from previous time step. And then our view of model predictive control changes. So ideal optimal MPC, we typically think about it as a static control law. So we take the state and we generate the control action. Now, if we do suboptimal MPC, we use fixed number of solver iterations per time step and warm starting, this control law becomes dynamic. So my optimizer becomes a dynamic controller that runs in parallel to my system. So the state changes. I perform L iterations of my optimizer for this updated state. I spit out the control, and the state of the controller is the guess for my solution, for example, for my optimal control sequence. And then the properties of this interconnection are going to be dependent of how many iterations per time step I'm able to perform. And so here's an example of an inverted pendulum on a cart, where with optimal MPC, where that is this problem solved to completion, I'm able to balance the stick. This is a pendulum on a moving cart. I can also do this job with 15 iterations per time step, but if I drop the number of iterations to 5 per time step, my closed loop system becomes unstable. I'm not able to stabilize it. Now, of course, this is a toy example, but these issues become important when you, say, try to land a SpaceX rocket that has somewhat similar dynamics. Now, it's possible to analyze this situation using a tool from control theory, which is called small gain theorem. And the basic trick is to rearrange the closed diagram as an interconnection of an ideal closed loop system based on model predictive control and the optimizer error subsystem. And the optimizer error subsystem has an input as a change in a state, and its output is the inexactness of the solution. So it's a disturbance by which your control action is performed. So it's an interconnection of these two systems. The other key step is to note that by increasing the number of iterations L that the solver can perform, the input-output gain, the asymptotic gain of this optimizer error subsystem, under reasonable assumptions can be made arbitrarily small. So then you want the product of two gains to be less than 1, and so you can find how many iterations you need for the closed loop system to be asymptotically stable at the origin and locally input to stay stable. You can also develop procedures to estimate this L star for certain types of problems, in particular linear quadratic MPC. The computations are quite tractable, as well as constrained regions of attraction. And we've been exploiting these procedures in a practical problem, including for spacecraft pointing with reactionable desaturation, stabilization of vehicle dynamics, and others. I should point out that the value of this bounds, L star, and the number of iterations that you need, these analytical bounds, they can be conservative. In other words, in practice, you actually need less iterations to get a stable closed loop. But the value of them is that you can examine the trends, and you can figure out how to modify your optimization problem and how modify your MPC problem formulation to reduce the number of required iterations. For example, if you increase the horizon of your MPC problem, you have more decision variables, and it's not surprising that L star typically increases. Now, suppose you want to lower L star, what could you do? Well, one of the things you can do, you can increase the weighting on your control in your cost function, make control more expensive, and L star is going to actually decrease. So there's some interesting conclusions that you can get. Yes, please.
Would it be a problem if you had to estimate the state?
That's a good question. I think you can definitely analyze this situation. We haven't done that.
Just an error in
Right.
the text.
Right. Yeah. So we do have LISS guarantee for that system, but we haven't. I don't think we have made it specific to the state estimate necessarily. Now, here's a third idea, or third approach from which we looked at the issue of computations and model predictive control, which is to say that suppose we are interested to solve our optimization problem to completion, but when is our solver really needs a large number of iterations? When is L needs to be large? Well, if your system is running in steady state and you're using warm starting, then nothing changes, right? The solution that you computed one step before is pretty good, and maybe you can improve it a bit by using one iteration per time step so that you have extra feedback. You don't lose the feedback, but that's pretty good. So if you look at where the spikes in the number of iterations occur, that typically happens when the problem data change. How can the problem data change? Well, the reference command, the command that you want to track, R, that you give to the system, that command can change, right? The pilot or the driver could give you a different command, and you have to track it. And indeed, you see the step in this pink dashed line, and this is where the number of iterations spike. So how to deal it? Well, how to deal with this? Well, you simply don't want to apply the step in the command. Maybe you apply a smaller step and then give it a ramp, and if you arrange things in the right way, perhaps you could run the system with just one iteration per time step. So this is an idea which is closely related to reference governors, and this is what we called a computational governor. And the idea of computational governor is to minimally alter the reference command to enable MPC optimization problem to be solved cheaply, efficiently, and reliably to completion. So I take my original reference RK, I pass it through the computational governor, it alters it to VK if needed, so that this model predictive controller solver can find the solution very, very efficiently. That's the basic idea. Okay, so how can we design this computational governor? I'll show you one development with some technical details, so you could see how this can be set up. I'm going to look at a special class of model predictive controllers called linear quadratic MPC. So the cost is what you have in linear quadratic optimal control. It's linear model, quadratic cost function on state and control variables. And in such a case, the optimization problem you have to deal with is a quadratic program. So here you had is the control sequence that you're trying to solve for. And this, the constraints of this problem become linear inequality constraints. And theta is a parameter. It's a parameterized QP. And parameter consists of your state xk and from your reference, which has been changed, v sub k. So that's the setting. Now, how do you solve an optimization problem like this? Well, you use Karush-Kuntaker's conditions, which is Lagrange multiplier rule. And this is a stationarity condition, basically that the gradient of Lagrangian is set to 0. S is a slack variable by which you relax the constraints, B lumps L theta plus little l. And then lambda are Lagrange multipliers that have to be non-negative. You remember slacks have to be non-negative. And then there is a complementary slackness condition, which is SI lambda I has to be equal to 0. But in numerics, we typically set it equal to a small number, and we decrease this number when we address these problems numerically. So this small number is eta, and we have to decide on it as well. Okay, now we don't like this KKT conditions because it's a system of both equations and inequalities. I don't know how to apply Newton's method to inequalities. So what you do is that you do logarithmic transformation. You define lambda is square root of eta e to the power gamma. Gamma is a log space variable. That's my new decision variable. And S is going to be square root of eta e to the power minus gamma. And so the product of them is going to be exactly eta, and they're both going to be non-negative. So that kills all of my inequalities. I just have equalities left. And to equality, these are my equations. And I can apply Newton's method that we just looked at before. So this is how the Newton step D would look like to adjust gamma. So gamma is a decision variable, D is a Newton step. And to determine Newton step, you need to solve the system of equations, linear equations. All right. Now, this is what's called logarithmic domain interior point method, or LDIPM. Now, what about this computational governor? Well, computational governor has a form of traditional reference governor. It's a linear interpolation between previous value of computational governor output and current value of the command. And the interpolating factor is kappa. That's something that we are going to choose. And we are interested in setting kappa as close as possible to 1, so this computational governor doesn't modify the reference one, it doesn't have to do it. Now, the question becomes how to pick this kappa. And it turns out that in this case, you have to pick kappa together with this eta, the homotopy parameter, by solving a linear program. It's a 2-dimensional linear program, so it's easy to solve. There are very special fast solvers for that. What you do is that you want to maximize kappa, you want to minimize eta, you want to bring eta to 0 as much as possible. So this is the cost that you're trying to minimize. Kappa is in between 0 and 1. Eta is within a chosen range. And the key constraint that you need to satisfy is that the Newton step D here in infinity norm has to be less than equal than 1. So this is a Newton step of first iteration, and this gamma k tilde is a warm started log space variable. So this is something that we determine from the previous iteration. There is a particular warm starting procedure that's being used. So it turns out that the Newton step D can be expressed as a linear function, or its infinity norm as a linear function of parameters. So indeed, this is a linear program. Now, why is it we want to do this? We want to maintain infinity norm of D to be less than 1. Because then nice things happen. You can show that then all subsequent LDIPM iterates are in fast convergence region and guaranteed to be primal dual feasible. So it has actually its similar property to robust early termination algorithm I talked about, except that this is now in iteration domain, not in continuous time. And then the feasibility, what does it mean primal dual feasible? Well, it means that feasibility is maintained even if you have state and terminal constraints. And horizon here, you could actually work with short horizon MPC that's okay too. So state and control constraints will be strictly enforced. So the idea is that the computational governor basically bounds the suboptimality of warm start by enforcing this constraint. And through additional analysis, you can show that nice properties, nice convergence properties that are usual in reference governor theory also hold for our computational governor. What do we see in terms of computations? We're able to reduce the computations by an order of magnitude in examples that we look at. We can also run with short horizon MPC and additional state constraints. The region of attraction is expanded. That's not surprising. That usually happens with the reference governor. But for conventional MPC, the region of attraction is backward reachable set of your terminal region, and that depends on your reference R. And when you use computational governor, your closed loop region of attraction becomes a union of regions of attractions for different values of the reference. That's a nice result, but it's not surprising. Some experiments in a lab here we are running this inverted pendulum in a cart. There are two screens. This shows the modified reference command and original reference command, as well as a true reference command. And then on the other screen, we are showing number of optimized iterations, and it's always equal to 1. So we are running with 1 iteration per time step, and you can imagine that in this case, computations are very, very simple, and we're able to satisfy constraints and do everything we want. Now, some of these ideas have actually been implemented in production with Toyota. This is a press release that if you'd like to read. So it's nice to have also some real-world impact. And to mention some of the additional and further work along these lines, we looked at this logarithmic domain interior point method, which is a nice way of solving quadratic programs. And we further developed it. One thing that we observed is that inside LDIPM, you have to solve linear system of equations that I showed, right? Well, do you really need an exact solution of that? Could you live with inexact solution? And we typically solve it using conjugate gradients. Well, you don't need an exact solution. And so if you set up inexact conjugate gradients, and this is always theoretical guarantees that we have, but in a range of examples that we've done in this paper, we have a reduction between 20 to 70% in terms of the computation time. So this is what we call inexact log domain interior point methods. And then I should point out that this idea of supplementing MPC and an MPC solver by some kind of supervisory scheme that keeps it happy, it seems like it's very appealing, and we've been looking at a number of other ideas along this line, in particular something we call iteration governor that not only modifies the reference command, but it also chooses the number of iterations a solver needs. We have a stability governor that enables the use of short horizon MPC without terminal constraints and with large region of attraction. Some versions of model predictive control use a preview, and we have a feasibility governor for preview-based MPC that facilitates implementation of such MPC with short prediction horizon as well as large region of attraction. And then something that we haven't converged on a name yet, even though we published already a couple of papers. I call it incremental reference governor, even though within our group we haven't uniformly agreed on a name. But the idea here is that we are able to set up model predictive control based on low fidelity model, and the reference governor then uses a high fidelity model to protect the solution against constraint violation. So we can basically, and we can do other things that combine this idea of designing schemes on low and doing optimization on low fidelity models, but then making sure constraints are enforced on high fidelity models. I did want to do time check, Professor Garoni. How much time do I have?
How much as you want.
Okay, so I'll then continue according to my plan. Let me just show you just very briefly stability governor. That's a scheme that is also kind of interesting. And what is the issue here? So asymptotic stability under MPC feedback is often guaranteed through the choice of the terminal penalty and terminal set constraint. So if you want to rigorously guarantee closed loop stability, what you typically do is that you constrain your end state at the end of your prediction horizon to a terminal region, and you also have to use a terminal penalty. Now, that's okay, except that in practice, this terminal constraint, which is shown in red box, is not something that practitioners like very much. One is that it's difficult to compute it offline. It complicates the online optimization because it can be quite complex, add some additional inequality constraints to your problem, which could actually be nonlinear in principle. And also its use can degrade closed loop performance because a lot of the control energy goes to satisfy that constraint. So people don't like it. Now, if you remove it, then it weakens associated closed loop stability guarantees. And in fact, it also weakens properties as well. So you could, your region of attraction can decrease. So what can we do in this situation? So let's look at this closely. Well, let's just drop this constraint, terminal constraint, and see what happens. So I'm going to look at terminally unconstrained LQMPC. And here I have the same problem that I had in the previous slide, but now here I drop the terminal constraint. The other thing I've done is that I replaced R, my reference, by V, because I'm anticipating that I'm going to use a reference governor-like scheme, and I will make this V different from R. Now, what happens for this terminally unconstrained MPC? Well, if you look at the case of linear quadratic MPC, so quadratic cost functions linear model, then it turns out that you can show that there is a region of attraction for this terminally unconstrained MPC, and it's given by a sub-level. This region of attraction can be computed as a sub-level set of your optimal value function. It's not surprising that sub-level sets of optimal value functions are regions of attractions. That commonly happens in MPC, and it happens in this problem. And the size of that set depends on parameter alpha, and alpha is what we call size of implicit terminal set that you can define. There are a lot of details here that are not important, but the important part is that this guaranteed region of attraction is typically much smaller than the region of attraction that results from a terminally constrained MPC law. So we lose something. We have a guarantee of, if we start sufficiently close, that will be stable, but it's a bit of a problem. So what do? We add a stability governor that's going to modify MPC reference command to maintain closed loop system in guaranteed region of attraction for the modified reference. And our reference governor, stability governor, looks like computational governor and looks like a reference governor. But the constraint it enforces here, it's a little bit different. It tries to maintain the state in the region of guaranteed region of attraction for unconstrained MPC, which is dependent on the current reference. So this pair of the state and reference command have to satisfy this condition. So this is basic idea. And what we see is that that's going to maintain stability for shorter horizon n and smaller terminal penalty lambda. Terminal penalty is something that also people don't like. And you get large region of attraction because with reference governors, you end up with a union of region of attractions for individual values of the reference. So that's not surprising. So that's the basic idea. You can work out the details. I'll skip it in the interest of the time. They're in the paper that we've published. But there is a way to generate implementation where everything is explicit and be able to show recursive feasibility, prove asymptotic stability, as well as finite time convergence of the modified reference to true reference. So there is usual theoretical guarantees that you would expect in this situation that we've been able to establish. Just to show a video, this is inverted pendulum on a cart. And here you see there is a red point which corresponds to a command for the cart position. And the blue point is the modified set point by the stability governor. And n is the horizon. So here I'm looking at the long horizon. And typically, the longest horizon, this region, unconstrained region of attraction, is going to, terminal unconstrained region of attraction is going to expand. But even with 85 steps, it's not enough. I'm starting outside of the region of attraction, and I'm losing stability. If I do stability governed implementation, you could see I'm perfectly stable. In fact, I can reduce this horizon to 50. Of course, the motion is a bit slower. So that's basically what this does. All right. If I have time to briefly touch on the last topic, it looks like I get thumbs up, so I'll continue. And very briefly, want to talk about connections with multidisciplinary design optimization, or more specifically with something that we call control-aware design optimization, where the problem is a bit different. What we are trying to do is that we are trying to look at design, in particular design of vehicles like aircraft or supersonic aircraft in our specific case study that we've done. And what we realize is that when we optimize its design parameters, for example, the wing shape, we often optimize it for things like fuel burn, takeoff weight, range of the aircraft. But there is also important characteristics of this aircraft that have to do with its ability to perform maneuvers. For example, I want to be able to take off and land. I have to be able to follow the glide slope when I'm landing. And if I'm hit by disturbance, I should be able to still follow the glide slope within the prescribed limits. So that problem, because the maneuvers depend on control, is somehow coupling the design aspect and control aspects together. And so the question is that then can we somehow define a control agnostic approach, ideally, that ensures vehicle controllability, ability to perform these maneuvers in the system design phase. So simultaneously optimize parameters while guaranteeing that there is a control that is going to do the job. Turns out that such problems can be reduced to bi-level optimization, where you're trying to minimize a function of design parameters, for example, wing shape, subject to a constraint on the value function of an inner loop optimal control problem, where this inner loop optimal control problem gives you the cost of your maneuver, right? And if you use penalty function, if the maneuver doesn't exist, then this penalty function will be basically very large. So the setting, this is a bi-level optimization problem. So you're saying that you want to minimize a function f of pp as a design parameters. And then you have a constraint, j star here is the optimal value function of your control problem at a lower level. And s has to be less than or equal than j bar. This is what we call this control-aware design optimization. So we have an MDO optimizer, multi-disciplinary design optimizer that adjusts parameters. And then we have a control optimizer that's going to worry about the maneuver here. Now, one interesting thing that we realize is that this bi-level optimization problem is not so dissimilar to what we have in model predictive control. And let me explain what happens in model predictive control. Let's look at this picture on the right here. We have a control optimizer that decides on a control sequence in MPC. That optimizer depends on the state, on the current state of your system, which is a parameter in this optimization problem. And this parameter evolves according to the plant dynamics, right? Now, what happens on the picture on your right, on my left, is that we have a parameter here as well. This is design parameter. And that parameter doesn't vary according to dynamics of my plan, but it varies according to dynamics of MDO optimizer. But otherwise, at this lower level, it's a very similar picture. So what does it suggest? Well, it suggests that some of the same tools that we use in control theory to analyze the picture on your left can be exploited for the problem in bi-level optimization in control-aware MDO. Notably, we can take advantage of small gain theorem and input-to-state stability to establish convergence guarantee of inexact bi-level optimization algorithms. So what basically this means that we don't have to wait for the control optimizer to converge while iterating on the design parameters. That's what basically this means. We can accept inexact solutions here. Now, can we make this precise? We've done a bit of work along these directions. In particular, if you look at the inner loop problem, being linear quadratic optimal control problem, this is in discrete time, which depends on this parameter p. And then under assumptions on the cost in the outer loop, we can look at bi-level proximal gradient algorithm, perhaps simplest algorithms of this kind. And we look at iterations in the parameter as well as in the control. And we can show that there exists a bound on the number of iterations in the inner loop, such that if you perform at least that number of iterations, this whole algorithm is going to be convergent to the solution. So we end up with a convergence guarantee. And the results, again, this convergence guarantees are obtained by using small gain theorem. Recently, we've been expanding this work, and in our inner loop, we now allow alternating direction method of multipliers, ADMM. And the nice thing about ADMM is that it allows us to handle also equality constraints in the inner loop, as well as it has a number of other properties. So we have now complete theory for that. And in the more fundamental way, from the perspective of the outer loop optimization problem, what is it we are doing? Well, we are basically doing some kind of gradient descent where we are relying on inexactly computed gradients. We are relying on inexactly computed gradients, and then we are able to establish convergence guarantees to the solution in this setting. So that seems to be an interesting idea, how to apply small gain theorem in other settings of this kind. And there have been a number of papers that we started to write, in particular for Newton's method for generalized equations, inexactness in bi-level nonlinear optimization. We call it gradient-free, in the sense that it allows the use of inexact gradients, and even some problems in game theory. For computations in game theory, we can exploit these ideas. So that does bring me to my last slide with a few closing thoughts. I talk about computations and model predictive control, and it's clear that inexactness of computations in MPC is going to affect closed-loop dynamics and closed-loop properties. We can derive bounds on the number of iterations to ensure closed-loop stability with receding horizon model predictive control. I haven't talked about shrinking horizon MPC. In shrinking horizon MPC, your horizon, your end time of your maneuver is fixed, and so the horizon shrinks every time you approach your end time, and that's of interest. For example, if you try to maybe do some kind of landing or waypoint following problem, and turns out that you can also do similar analysis for the shrinking horizon MPC and get various bounds on the number of iterations that you need. Supervisory schemes for MPC can be developed that improve reliability of MPC with short horizon, reducing computational time and expanding the closed loop region of attraction. I think I spoke about at the end that analysis of inexactly solved bi-level optimization problems in MDO can benefit from control-theoretic tools such as small gain theorem. And finally, I should point out that much can be learned from treating application problems in different domains, and it's a rich source of challenges, but also ideas of various things that you can try that they can later, some of them can actually lead to some interesting theoretical developments. And I'll stop here.
Okay, now it works. We have time for questions. Paolo?
Thank you for the very nice, interesting presentation. So I was wondering, when you calculate L star, that is the minimum number of iterations that you need. I think I probably missed some details about the guarantees that you get and also the problem setting. Is persistent feasibility included in the guarantees that you get?
So let's just say the current results. So the existence, there's two different types of results. The existence of L star can be established in a more general setting than specific bounds on L star. For the specific bounds of L star, we typically look at linear quadratic MPC with control constraints. That's the easiest case to analyze, in which case the issues of recursive feasibility, they're very easily satisfied because you only have control constraints. Then, as a next step, what you can do is that you can establish a region of attraction or a region such that if you start from that region, then all other guarantees, including recursive feasibility, will hold. So that's how the current state of the results. And I'll be very happy to show you, I have 3 slides to show actually how we estimate L star based on linear quadratic MPC.
And I think you said that, right? But the price you pay is that the region of attraction gets just smaller, right?
You know, this is a very interesting, the behavior of region of attraction with L star, it's a little bit non-intuitive. So in other words, it's almost like, at least in a linear quadratic MPC setting, if you look at analytical bounds, it's almost like this, that for some value of L, you don't have it, and then you have it.
Ah, okay.
So it's kind of like this. And this is, we've been looking at this problem, but some non-intuitive things happen, at least with the type of bounds that we are currently using. But yes, it's roughly speaking, what happens is that you need to have a contraction somewhere. And in a linear setting, linear models, quadratic cost setting, you know, things start to look more and more like linear, and so you either have something less than 1 or not. I think in nonlinear problems, you can have more interesting behaviors.
Right. Thank you.
Other questions? Well, I will make a question for which I already have an answer, but just to provoke you a little bit. But are we sure that with the technological increase of availability for what concerns computational power, it is relevant to look into reduction of the computational cost of MPC?
You know, I think it depends on applications that you consider. And as I said, you know, if you look at quadcopters at the moment, they are fairly computationally limited. And that question has to really be answered in strong connection between applications that one might have and computational hardware. I should also point out that the speed is one aspect of this whole area of research, how quickly you can compute the solutions. But the other one is reliability of computations, and that becomes important, especially when you deal with nonlinear MPC problems, because then, you know, you can have all the time in the world to compute, but if you converge to wrong solution, then that's also doesn't do you any good. But yes, I would say that as I see cases where there is there's definitely growing computing power. One thing that you have to also realize, that at least my experience in industry is that, yes, you know, the computing power grows, and you know, there has been Moore's law, right? Or I forgot what's the name of the law, but essentially the number of transistors doubles every 18 months or something like that. And what I've seen in industry is that sometimes, while this is true, you tend to keep the computational power about the same or grow slower, but then actually transfer some of these improvements into cost reduction. So basically get, like in automotive, you might want to get a lower cost module, which will be a bit more capable, but maybe not as capable as as you'd like to have. So at least at the moment, I see across a range of applications, computations being, in terms of speed, being an important limitation. What happens in the future, it's hard to say.
So if there are no other questions, are there other questions? Oh, Frank.
Thank you. Wonderful presentation, very interesting. I see, of course, that safety critical applications is a clear domain where you apply this kind of methods. I was wondering if you could let us know something about the application of these methods to nuclear systems. So, for instance, for the prediction of criticality, evolution, and how to control this. Thank you.
So this is very interesting. I'm not an expert on nuclear reactors, for example, control. I had interest in this type of problems from general application standpoint. And what I realized is that many reactors are made very safe by design. That is, the control task is made simple through the design. And so, and partly, you know, this is just because of the technology involved. I don't know if things will change with some of the more modern, like a small modular reactors that people are considering. And I think there's a range of other possibilities where ensuring safety is absolutely critical. But I think the control, the reliance on control, at least at the moment, my sense is that it's not as heavy reliance on control, because really they are made safe by design, I think. That's my impression. But as I said, I haven't worked on these problems, but this is just my impression from talking to experts and
Thank you, Ilya, for the presentation. I just maybe missed the detail. I think it was with the battery of electric vehicles. I wonder, you said that you ensure reliability of the long-term prediction using what? Yeah, with the battery for the electric vehicles example.
Yes.
I think it was fairly at the beginning of the presentation. You said that you ensure the reliability of the long-term prediction using...
Yes, so the key question in its setting, the key question for us was, can you predict the vehicle speed sufficiently far ahead? And the reason is that the thermal dynamics are slow, and so you'd like to, for example, predict the vehicle speed 5 minutes ahead. And so initially we were skeptical, because the previous work we've done, for example, for hybrid electric vehicles, we could do it 10 seconds into the future, and that, if I remember the numbers correctly, it gave us between 1 to 2% improvement for HEV energy management. But tools since that time and ideas have advanced, and so we looked at queuing models for short. So this is in urban driving scenario where, for example, we drive through, let's just say, 5 intersections with traffic lights, and we are assuming that we have tons of historical data. What we're interested then in doing, and in fact, you know, near University of Michigan, we have so-called Plymouth Road that has a very notorious 5 traffic lights where there's a lot of traffic jams, and depending on time of day and day of the week, different things happen. So we have a lot of data for that. And so what we found is that by utilizing different techniques over different horizons, in particular queuing models, which are more kind of first principle based models for short horizon, and then using a neural network and then Bayesian network predictions, where we update so for example, one thing we have found is that if you condition your prediction on whether the vehicle stopped at the first traffic light, then your accuracy increases quite dramatically. The other thing is that if you do it on spatial domain, that is as a function not of time but of distance, that improves things as well. So with a number of these observations and sort of using some of the tools with Bayesian networks, we've been able to get reasonably good accuracy for those applications where we can demonstrate energy efficiency improvements. I'd be very happy if you send me email. I'd be very happy to give links to papers where these developments were reported.
I would love to. Thank you.
So Bruno,
Thank you, Ilya, for the presentation. I tried to keep count of the publications that you had in the last couple of years, but I ran out of bits by half time, which is great.
It's not always good.
Well, good publications, not just publications. So, so you stressed a lot about the impact of the inexactness of computations, right, with regard on stability and other properties. Is there any work that relates the explicit MPC kind of results to stability, for instance, right? Which addresses also the question that Emanuele asked, right? When you don't have the computation, you might just, rely upon, storing the solution and then just having to retrieve it. Is there any relationship between stability results and the coarseness versus the fineness of this?
Yeah, there has been, definitely there has been work on trying to understand if you have an explicit solution and you have approximation errors, could this translate into instability? And I have to remember the references, but I know where to find them. So right, yeah, it's, well, anyway, I have my memory on recall is not great, but yes, this work has been done. Now, one thing that I should point out that certainly when we started looking at these ideas on automotive side, which is around 2000, it appeared that explicit MPC was the way to go because you don't have, I mean, it's easier to certify, you know exactly what the computation time. But what transpires is that when you store, your computer store the solution, the solution can be quite complex. And even in linear quadratic MPC setting, you have a lot of these polyhedral regions as well as gains. And so the time to go through these regions and just to find the right one for higher order systems, maybe with 4 or 5 states already, can exceed the time to perform a few iterations of online optimization. Now, people have done various approximation schemes, how you can eliminate some of the regions. For nonlinear MPC, there has been work approximating such solutions with neural networks and with some kind of nonlinear approximators. But my sense is that you're fundamentally against the curse of dimensionality limit, that you're storing multidimensional function, and that's difficult for high-dimensional problems. Now, if the problem has 2, 3 states, maybe not many constraints, then I think that's quite feasible.
Yeah, and I would say if the gradients are not too high, maybe you can compact.
Exactly.
Yeah.
Exactly. But how to do it systematically in high dimensions? That still is a challenge. I mean, other ideas people, for example, have tried to take advantage of symmetry of the problem. For example, about different axes, and you could kind of generate solutions about 3 different axes, and then that gives you total control law. I think always new ideas can be found, but I at some point convinced myself that you are kind of against this curse of dimensionality type of a limit to develop a nonlinear kind of nice, easily parameterizable nonlinear approximation. Again, things are evolving and nothing remains cast in stone. If there is a deep neural network that somehow does everything, then that's a different world. So.
I also had a follow-up question concerning, you mentioned before, Bayesian network predictions, was it, if I'm correct? Actually, what is it more precisely, and how does it work?
Well, so the idea is that you essentially define conditional probabilities that, of your prediction. If something happened in the past, what's the probability of what's going to happen in the future? And so you build sort of a sequence of events. For example, am I stuck at my first traffic light, right? Am I stuck at my second traffic light? Am I stuck on a third traffic light? And then if I have historical data, I could estimate the probabilities of getting stuck and probabilities of what's going to happen. So it goes back to ultimately to Bayesian inference and Bayesian rule for basically a posteriori probability estimates.
And what now if you don't have enough historical data? Do you kind of try to construct kind of like to make a prediction, how you can you compensate if you don't have historical data for like situation you didn't expect?
Well, so very good question. You know, I can only give a generic answer because I think a lot of things we've done are really heavily tailored for historical data. And in a vehicle driving context, you can instrument traffic lights and see cars passing by, and you can kind of collect those data. You know, generally probabilities, you could interpret them also as reflecting of your beliefs. And if you have reasonable beliefs, you can still configure those models just based on somehow intuition. But I think it's much harder to do. So.
Okay, so I imagine there are other questions, but at a certain point I have the task to close it here. I'd like to say a last thing that is reporting a private conversation between me and Ilya, if Ilya allows me, but he doesn't know what I'm going to say. So that is so. 2 years ago, when Ilya was here with us for a month as a chargement, when he went back home, I remember that we had a call and he said, you know what, when I left Brussels and I arrived here, I felt like I left a familiar place and I would be very happy to come back again. I hope that he will say again something like this in a few days when he will be back home and that we can have him again as a guest here.
Absolutely, I predict that will be the case. And again, thank you so much for organizing the program. It was a real pleasure to be here.
Thank you to you, Ilya. So a last round of applause. And at this point, I invite you all for a coffee, and after that, we will have our second speaker. Okay, so welcome back for our second seminar of this afternoon. So it is really a pleasure for me to introduce the next speaker, who's Professor Sinopoli from Washington University in St. Louis. Now, before speaking about the career of Bruno, let me tell you that sometimes there are people that have superpowers, and Bruno is a person with superpowers, in the sense that since I know him, he is someone who sometimes starts a subject. The subject at the beginning, nobody believes in it. And then 1 or 2 years later, it's always one of the big things in our field. So I've seen it happening for control over networks. I've seen it happening for cyber physical security. I've seen it happen also for other subjects. And so a little request to my researchers in the room: please take note of what Bruno is doing, and let's try to go with the wave, because historically we have a good data set that that's what's going to happen. It's going to be the next big things. So besides that, so Bruno is a very dear friend, was very important for me at the beginning of my career. He has an excellent career. He did his PhD in Berkeley, postdoc in Caltech. Then he was a professor at CMU, at Carnegie Mellon University in Pittsburgh, and now is department chair at Washington University in St. Louis. So he has said he is author of several very influential papers, and it's my pleasure to give him the podium so that we can steal from him ideas.
Thank you, Emanuele, for the kind introduction. Thank you all for being here. I also want to thank BrIAS for hosting me here in Brussels. This is a fantastic idea. It's bringing together scholars from all over the world around interesting topics. I think it contributes, I think, to not only to the visibility of the university, but also to science in general. So I'm very happy to be here. And thank you, Emanuele, again for the introduction. I'm actually here to learn, so I don't think I have anything new to offer here, right? And to Emanuele, I have to say that I think you have learned quite well, right? Your research spans, entomology to batteries. So I think you have your own way of discovering new fields under the lens of systems and system theory. Okay, so today I want to talk about a project which we started about a couple of years ago. And it stemmed from the observation that these days tools such as neural network, deep neural networks, or more generally AI, you hear all the time, right? AI will take care of it. What does it mean? AI will take care of it. As if AI was this deus ex machina who could solve all the problems that you had, right? At the end of the fair, this AI is nothing but a number of techniques or regressions, right, that uses large amounts of data and very often is an overkill for problems, right? And it substitutes often what we can do through analysis, right? Instead of trying to exploit structure in problems, we just hammer it down with these huge tools in the hope that they will give us the right solution. So with this mindset, we started looking at problems of dimensionality reduction, right? Dimensionality reduction has been a problem that's been existing for over a century, right? And that these days completely dominated by nonlinear methods, okay? And so we wanted to revisit this to see whether actually the current approach is the right way to go, or maybe there is something that we can still recover from or learn from linear methods, right? And whether by adopting linear methods can provide some advantages, okay? First of all, let me acknowledge so this is, first of all, joint work with my colleague from computer science, Professor Netanel Raviv. And by the way, which reminds me that my postdoc I did at Stanford, not at Caltech. I don't want to create, since this is recorded, it's better to be precise. It's okay. I spent time there, but never. So this is main work was done by our joint PhD student, Baharam Yaguti. Okay, and so this is what I'm trying to. First of all, right. Let me ask about the background. Right. How many people are in engineering here? Okay, not everyone. Okay, and how many people are comfortable with linear algebra? Okay, good. That's all that you need for this. So right. So what we're gonna set the problem of dimensionality reduction. We're gonna very quickly review some of the existing linear reduction methods for, we call it also feature extraction, right, in common data science, right? And then we'll provide an idea or a general approach to solving these problems, which we call iterative redundancy removal, right, which is basically based on Gram-Schmidt methods of orthogonalization. That's all that there is to it. So not only linear algebra, very simple linear algebra. Right? And we show, what I'm going to try to do is convince you that methods of this sort provide a lot of advantages over, the neural network-based methods. And to do so, we'll show in the context first of the usual academic data sets, and also a very specific example which is related to genomic, right? Thanks to the data provided by our colleagues at the medical school at WashU. Right? Okay. So let's set up the problem, right? Problem dimensionality reduction. You have data, right, which are points in RD, let's say, and your goal is somehow to compress this data because you want to do something with it. You want to process it. You want to do some learning. You want to do transmission. Therefore, you will benefit from a smaller representation of such data. Right? And so the usual approach is to project such data to a lower dimensional space. Right? You want this to be fast. Linear is usually fast. And the most important thing is that once you throw away some of this data, you want to preserve the informativeness of this data. You want to throw away data, but not information, right? As my mom always said, you never throw away information. In this talk, we'll look at the problem of unsupervised feature extraction, and also we'll see how the extension to the selection is actually quite simple throughout these methods. Okay, so let's say the data belongs to a subspace of dimension n, which is much lower than d, right? So that there is, in other words, redundancy in this data. And this redundancy is as nonlinear redundancy, right? If the redundancy was linear, we know already what the solution would be. Okay, so it's of this sort. If it's linear, PCA provides the optimal algorithm in order to remove redundancy. So there's a lot of dimensionality reduction methods, right? Of course, everybody knows about PCA. PCA is still used in a widespread manner in sciences. Right? When we talk to our colleagues doing genomics, which is actually a very interesting problem, where you have very little data, very many features, they still use PCA, and there are advantages to it, and I will touch upon it, especially in terms of interpretability of the data. Right, because PCA preserves the global structure of the data, so you do not, and that provides cues as to interpret such data. Locally preserved projections, which preserve local neighborhoods relationship by projecting the data based on the graph structure or the points that are nearby. Independent component analysis, which separates the data into statistically independent components. Then there's kernel PCA, which extends PCA using some kernel trick to capture these nonlinear structures in the high dimensional spaces. And then there are methods which are related to the most recent data science, like UMAP, which are nonlinear techniques that preserve both the local and global structure, and autoencoders, which are just neural networks. Okay. So what is the problem, right? Dimensionality reduction can be applied broadly to two problems. One is feature extractions, right? Feature selection, where basically you choose the dimension or the features as they are, right? You have a number of features and you select some of them, right? While in feature extraction, you compute new features as combination of the existing features, right? Right. And you can provide some information theoretic guarantees. Conditional entropy, for instance, is small, right? If it's small, basically you are basically preserving the informativeness of the original data by simplifying it, right? And as I said, in this talk, we'll look at no labels, right? And the popular methods which are used today are this kernel PCAs or deep learning methods such as autoencoders, right? And if you go to these conferences like NeurIPS or AI Stats, methods of this sort dominate really to the extent that if you propose linear methods, and I've learned that on my skin, they are disregarded as old stuff, which is irrelevant. That's fine. Okay, so what we want to do is develop methods, linear methods, right? So linear combination of the data, which are able to remove nonlinear redundancies in the data. That is something that PCA cannot do. Right? It cannot remove nonlinearities, right? And nonlinear methods can remove nonlinear redundancies, but the methods themselves are nonlinear. And deep learning, of course, can be applied. It can be applied to anything, but you'll agree with me that it has robustness issues, right? There's a lot of data, and very poor guarantees or no guarantees are provided. So we wanted to address all these issues, right, by proposing algorithms that identify a non-redundant linear projection of the data. And so in this way, get the best of both worlds, right? Preserve linearity, which provides all sorts of advantages, but remove also nonlinear redundancies, right? And these are some of the goals that we aim to obtain, right? Simplicity, which using the reductionist approach in science is always something that you want to achieve. And we want a systematic approach, not something where you have to fine-tune possibly hundreds of parameters to the particular data that you have, right? And that is deep-rooted in the fundamentals so that we can get some guarantees, right, and a clear direction. Something that is robust and again is low and not very sensitive to the choice of these hyperparameters. Right, and the other thing is provide explainability, which is very important for science, right? And ultimately, right, we want to have a empirical performance which is comparable or better than the existing methods, right? So the general idea is. Right, we have the general idea, which I will explain in a couple of slides, which on one side will provide some practical algorithms that give information theoretic guarantees, right? And the guarantees that you get are always in the sense of conditional entropy, right? On the other hand, and I will focus much less on this, there are so-called theoretical algorithms. We call it theoretical because it rests on some assumption, which is difficult to validate from the data because you don't have the distribution, you usually have the data. But these theoretical algorithms can guarantee that if you had, if you were able to verify some assumption of the data, you could exact guarantees. You could guarantee to remove all the redundancies in the data, which is actually pretty cool. Okay, so this is the general idea, right? This is a meta algorithm, right? So let's take the data. Let's say that this is IID from X, and find this informative linear projection, right? So as I said, the hypothesis is that our data set contains redundancy, right? Which is a sum of independent random variable and their function, possibly nonlinear function, right? So the general framework is the following. It's very simple. It's rooted in linear algebra. Project, subtract, and then repeat, right? So an assumption that you'll make is say that the redundancy is captured by a family of functions, right? F in some, these are generic variables, y1 to yd, which is the dimension of the data. Right? We'll see how you don't really need to know precisely the redundancy, right? But if you pick a rich enough functional space, right, then this actually will work quite well. And so, according to some methods, which will depend upon the specific algorithm that you will pick, you'll find some direction at iteration j, vj, which is some variance maximizer of some distribution, right? And you define a new variable, which is zj, which is generated out of this product, is a new random variable, right? And then what you do, you do subtraction. So you orthogonalize this family function where you keep all the functions up to variable yj, right? You substitute the z to the yj, right? So you take this family of function, right, and in such that depends only on the first j variables, right, to get an orthogonal set oj. And then you subtract this oj from the data to create a new random variable, right, which you call dj plus 1 of x, right, which is just a projection, right? And then you repeat this routine, right? From j, there goes 1, right? Potentially, you could go up to d, but that would kind of defeat the purpose of dimensionality reduction, until you meet some condition, right? That usually is some variance threshold, right? Basically, you're saying I keep orthogonalizing until there's very little information left in the residual data, and I'm happy to give it away, right? Right. So this is the general idea of iterative redundance removal. So and so let's look at the algorithm at the different pieces more in detail, right? The tool one is what we call Gram-Schmidt orthogonalization, right? Which is this routine. Right. So basically, you find this variable one by one at each iteration, right? And basically, you orthogonalize f, which is our functional subspace, variable by variable. Okay. Where fj, as I said, is a subset of f, which depends. Which contains all the variables which depend only on the first j variables. Okay, and then you call this orthogonalization routine, which basically appends the new functions, which are the functions that depend on the jth variable. Okay, And for all the g's that belong to fj but not to fj minus 1, so these are the variables that contain the jth variable, then you add the following function to the orthogonalized base, right? Right, you can see this as simple vectors, and this does not change. Of course, you have to compute expectations, and you don't have the distribution, so you can just substitute with empirical means. Okay. The second is, how do you choose this direction, right? In order to define the new variables, right? Intuitively, you do in such a way that this variable represents what remains in the data after you have removed the span of the OJ, right? Whatever is left, right? And you can define these alternative covariance matrices, which is nothing but the covariance matrix of the new variable, of the variable dj that you just created, right? And this can be computed inside the orthogonalized routine, right? And so you choose this new direction according to this covariance matrix, right? And then then it's complete. You have everything in order to continue. Okay, so let me connect this to PCA, and hopefully this will shed a little bit of light on why we're doing this, right? So PCA project the data on the large eigenvectors of the covariance matrix, right? So that's what it does, right? The kth component can be found by subtracting the first k minus 1 principal components from K, right? And in fact, if you choose your family function in our approach to be the singleton, right? So you remove all the nonlinear functions from this. Basically, you can say that our algorithm generalizes, specifies to PCA. So in other words, what we propose is a generalization of PCA, where in this family function, we include all sorts of combinations, nonlinear combination or functions of the singletons, right? Which could be polynomials. This depends upon your choice, right? Especially if you have some prior on the data. Okay. So this is the general approach, right? Now let me give you an idea of some of the algorithm that we use, right? And the first one is we call Gram-Schmidt functional reduction, for lack of a better name, right? So it's an implementation of the general idea of iterative redundancy removal without any assumption on the data. So you get data, you don't know how this data was generated, right? All you have to assume, which is kind of, I think it's a fair assumption, some constraint on the energy of these functions, right? Which is fine, I think, right? So this is how the algorithm works, right? You take this data, IID again from an unknown x, and you define a threshold. The threshold is your stopping criterion, right? How much information you can afford to leave or to lose in this process. Okay, and the output is all the extracted directions, right? Up to m. M, of course, varies depending on m is a function of epsilon, right? The smaller the epsilon, the larger the m, right? Because you want to refine more and more the data, right? So you initialize your first covariance matrix as being the covariance of the data that you have, and of course your subspace is the empty one, right? And then you run the routine from J1. I mean, you could put a while loop, it doesn't matter, up to D. You take Vj, and this is what specifies Gram-Schmidt functional reduction, to be the largest unit norm eigenvector of this covariance matrix. Okay. Now, if this condition is satisfied, right, then you have basically met your threshold, right? And you end the algorithm. Right? If not, then you define the new variables, as I said before, and you run your orthogonalization routine, right? Which will give you the new subspace and the new vector. And based on the new vector, you get the new covariance matrices that then you will use in order to define the new vector. You just iterate. I'm going to leave it there for a second. It turns out this provides some information theoretic guarantees. So if you take x and epsilon to be the inputs to the algorithm and the vectors to be the outputs, then you assume also that your z to be the new variables that you use in order to instantiate the functions in this functional space. You assume also that you have a finite alphabet, which I think is fine, right? So we have a theorem that says that the conditional entropy is bounded by this quantity, where d again is the dimension of your data points, right? And in order to prove this, it's just a bunch of bounding that you do, right? By the conditional entropy, you can bound it by z orthogonal. And which ultimately you bound by the sum from J M1 to D of H of the entropy of Zj. So all the variables from M to D, the one that you're not using. And so also orthogonalization we know increases entropy. So you can bound this H of Zj with H of Z tilde J, which is just the orthogonal of Zj, and then you can bound again this quantity by epsilon squared, which basically gives you the result. Okay. So that's a guarantee that you get. Okay, but now enough of theory of linear algebra. So let's see how this performs. Right, and of course this is a dimensionality reduction, so you have to instantiate into some problem to be able to characterize the solution, right? And so we apply to classification problem, right? And so you want to compare on the basis of classification accuracy. Right? So as you said, remember one of the goals was having a performance which is comparable to existing methods, right? And then with regards only to PCA, see what residual variance is left in the data, right? And here the goal would be to have the same residual variance with less features, right? And which would say that, given that we start with a different family function, we can achieve the same informativeness of PCA, which much less, with many less features. Okay, right, which is basically what I said. Okay, right. So these are comparisons with this COIL data set, Columbia, I forgot what it means. Anyway, it's one of the standard data sets that you find, right? And here we are comparing the classification accuracy of support vector machines with where we choose a radial basis function kernel. Okay, and we are comparing GFR, which is the method that I just described, with linear methods. That's an apple-to-apple comparison. And also with kernel PCA, which is apple to oranges, because kernel PCA is nonlinear, right? Where we use the same functional space. And here are the results. So our method is in blue, and as you can see, it consistently outperforms all of the other existing methods, including kernel PCA, right? And the gap is well, I don't know that I can say, right? Where on the x-axis, there are different performances as a function of the extracted features. Okay. And you can see that the gaps become wider as we choose less features. Okay, which. And we have performed other examples with USPS data sets, only to get very similar results. So this is actually a comparison with autoencoders, so neural networks, and UMAP, right? Which are the state of the art if you talk to whoever is anybody in data science. And this is very interesting because I think it speaks to one of the other properties of our algorithm, right? First of all, here this is our accuracy, GFR, and this is the accuracy of UMAP, and with respect to two data sets, NIST and again the COIL 20. And on the bottom, you'll see the comparison with under the same data sets with autoencoders, right? And what you will see, first of all, right, the results that we get do not depend upon any parameterization, right? So you don't have to fine-tune any parameters. It's very fundamental and very systematic, right? Whichever the data, you apply the same algorithm, right? Which is something that you cannot afford to do when you use these methods, right? As a matter of fact, this variability this is some quartile or some, which I don't know, which I actually don't remember what it is. But this is the average performance, but you will notice that, and this is the variation that you get depending on the choice of hyperparameters. But what is interesting to notice is even with the best choice of hyperparameters, which is something not to be taken for granted, we do better than UMAP, than these nonlinear methods. Was this enough to convince the NeurIPS community that this was a worthy algorithm? No, we got to reject it. Okay. Right, so that's the first. Then let's compare to PCA in terms of variance reduction, right? So in PCA, you extract this M dimension, and which are the eigenvectors of the covariance matrix sigma with these eigenvalues, right? And bound residual variance, you use the largest eigenvalues of from m plus 1 to LD, right? Of the ones that you're not extracting. In GFR, which is our algorithm, the residual variance is bounded by epsilon, right? Used to threshold the variance at the jth step. Is it mine? I don't know. It was some alert. Actually, 2 weeks ago, the tornado blew through our neighborhood. We were one of the few houses without damages and without losing electricity. So hopefully it did not happen again. Anyway, so this is more important. Okay, so all right. So here, let me give you the results. So for identical epsilon, so that we compare, it's a fair comparison, right? Which is the threshold or remaining eigenvalue, right? You will see that GFR extracts much fewer direction than PCA, right? And this is up to an order of magnitude, right? So on the x-axis, you see the epsilon, right? Which is the remaining, it's a proxy to the remaining information that is left in the data, right? And when epsilon is equal, you will see that, right, the GFR, and here we compare GFR with different degrees of polynomial. Remember, you get to choose your family function. Of course, the richer the family function, the more information you can extract, right? And that's why you see that the one with polynomials of degree 4 achieves the better results, right? But here it's up to an order of magnitude, right? Basically, with much less features, we can extract the same information as PCA. So as I said, I'm just going to allude to, right? We have in our paper, and if you're interested, I'll point you to it. It's in the archive. It has been submitted actually to Transactions of Information Theory. Hopefully, will be accepted there soon. This is the theoretical algorithms I was alluding to, right? And if you make this assumption of the data having these epsilon redundancies, which is something I don't want to really go into details, we can guarantee that the conditional entropy is actually 0. Right? Problem is that you cannot really apply. You don't really know whether the data that you have satisfies this condition. Okay. The other thing that you can do is, and I'm going to go quick, you can apply very quickly these algorithms to feature selection, right? Where basically what you do, instead of, you have to solve a different optimization problem, which is integer problem, because instead of finding the combination of the vectors, you have to select them, okay? But the structure, this iterative redundance removal, stays the same. Okay. All right. So up until now, we have developed a number of Gram-Schmidt algorithms for dimensionality reduction, where you fix a set of functions f, you project, orthogonalize, or subtract and repeat. Right. So this GFR applies to any reasonable distribution. It's a linear method, right? And you can see it as a probabilistic or nonlinear extension of PCA, right? And we showed that it's competitive against state-of-the-art linear methods and some nonlinear methods as well, right? And you provide guarantees, right? You provide guarantees. It performs well. It's simpler, and it's robust, as you can see, because you can have hyperparameters, right? And this GCA, which I did not get into, right? It's really the perfect feature extraction algorithm, but it is in an ideal setting, right? And both can be used for selection. Now, I want to give you an example of why I think this is important for explainability. Right. So we started working with a faculty in the medical school who works on genomics. They provide us with data, brain cell data set, right? And the goal would be to achieve biological interpretability of extracted features. Right? So we have a very sparse data set, right? We have a data set with over 53,000 features, but only 7,000 samples. It's a very tough problem, usually. And these are the problems that you usually encounter in genomics. And so what we did with two things. We applied PCA to the entire data set to extract 20 components. Right? For each of these 20 components, we selected the first 100 features, so the 100 features with the largest coefficients. Okay? And the second method is, instead of applying directly PCA to the data, we applied our feature selection to the data set to select a much lower number of features, like about 7,700 features. And then we applied PCA not on the entire data set, but on the selected features, right? And then we did the same thing. Selected feature, selected 100 features with the largest coefficients in each component. Okay, and then what we did, we performed gene ontology analysis on the selected features from steps 1 and 2. Basically, we looked at the feature extracted by the two methods, and we see whether these features are compatible with what we know about brain cells. Okay? And this is, so I'm going to show you a little bit the results. This is a map of the more important features, and this is just graphic. I don't pretend that you look into anything. It's just a graphic representation to see how the two methods provide very different importance in terms of features, right? They're drastically different, right? And just visually you'll see, right? I mean, the bigger the circle, the more important is the feature, is the feature, right? To a certain cell. Right, and we can notice also here, right? So on the left, you will see the method that we applied, right? By reducing first the number of features via selection and then applying PCA, versus the method number 1, which is applying to the entire data set. And so we ran it through our geneticist, who confirmed that some of the features, that all of the features extracted by our methods are relevant to brain data cells. While some of the features which were extracted by the methods that just applies PCA blindly reveals some features that are not expected gene ontology terms. They're nearly not relevant to brain cells, and this is known. This is prior information. Right? I hope this convinces you that methods of this sort can enhance interpretability. The last thing is, in terms of interpretability, which connects to to neural networks, is enhancing convolutional neural network interpretability. Right? There is this method called class activation mapping, which is a technique which is used to visualize region of an input image to which regions of an input image are the most important for a deep learning model's prediction. Right? So we applied, again, a method of similar, which we call GSF-CAM. So basically we use feature selection to select features from the features map to test to the last convolutional layer of a CNN. Right? And the residual variances of the selected features are calculated and then normalized to have unit norm. And then the normalized residual variances are used as the weight to generate the heat map, which gives you a map of the important features in an image. Right? First of all, analytically, right, we compared the method that we proposed to other CAM methods, right? And this average drop percentage, right? Don't ask me what it exactly means. What I know is that lower is better. And our method is the one that achieved the lowest average drop percentage. Actually, it's written here. The average decrease in the model's confidence when predictions are made using only the key regions of the input influence the original decision. Okay? And so this is what we did. You have a convolutional neural network. You apply to the last layer GFS. And then you generate your heat map, and then you overlay your heat map to the output, right? And this provides you with a graphical way of seeing what are the more important features, right? In this case, for recognition of the animal, right? And these are just some other experimental result, where we used ResNet XT50. Right? This is what you can do. Right? Okay. All right. So future work. Right. First of all, it's not really clear why we achieve similar performance to nonlinear methods, because in theory we should be doing worse. Right, so I think it is important these days to do more comparisons with deep learning methods in terms of robustness and the amount of data, and extend some of the results to other functional spaces. For instance, non-polynomial redundancy. Right here, we always use polynomial family functions, right? And also relationship to this tool called canonical correlation analysis. We'll also say that, given that our background is in systems and dynamics, I would love to look at possible application to model reduction, especially when it comes to PDEs, which of course contain naturally a lot of redundancy, which is given by the tight coupling that you have, whether it could be applied to problems, I don't know, in fluid dynamics and the likes. And here are some references. The main paper is, you can find here on the archive, and which is under review by, as I said, transaction of information theory. I have to say that a lot of the stuff that we did, like this CAM comparison or the genomic analysis, is not in any paper yet because we haven't published it. All right, with this I will conclude, and I thank you for your attention. For online, not for.
Thanks for the presentation. So I have a question about your the example, the genomics example. So you said you have 50,000 plus feature and 7,000 samples. This means that you can't even train a neural network. Am I understanding correct?
I think it would be extremely difficult.
Yeah, well, so it's basically, that's why you didn't have any comparison, if I'm correct.
Yeah, people use PCA in this field still.
Okay,
still
so that's the dominant technique when it comes to this, at least this field of application.
At least our colleague who regularly publishes in Nature and surrogate journals, what he was previously using was PCA, and that's why he was so interested in the techniques that we've developed. Yeah.
Okay. Okay. I have other questions for that.
Go ahead.
Okay. So one argument in favor of using neural networks when it comes to classification of feature extraction is the flexibility. Now, how difficult is to define because I think it's up to you to define the vectors V1, V2, Vm, right? Mm-hmm. For a generic application. I mean, for instance, in the genomics example, I guess when you show the table, each of the end of the rows of the table was associated with a V, right? With a vector V.
Yes.
Then the question is a kind of systematic procedure to do this, to code, or you do it manually? I mean, that's...
Yeah, this is systematic. What is not systematic is... right. Yeah. To choose, for instance, how many features to extract. We extracted 7,000, but this could be an iterative process.
But isn't that given by what you're looking for? I mean, you want to extract a certain number of features. You know what you're looking for in the data, right? That's not user-defined in a way.
What do you mean? You don't know what you're looking for in the data. I mean, in this problem, this was just a demonstration, right? We had some prior knowledge. We wanted to test our algorithm against this prior knowledge. And that's why we cooked up this.
Okay.
This example, right? To see whether, right, in fact, the methods that we use are more explainable, right? And that was the reason for prefacing PCA with GFS. So in the hope that it would remove a lot of features that are irrelevant, so that PCA does not then...
That's basically the comparison should last, right?
That's right.
Well, the two steps.
Yeah.
Okay. Thank you.
So there was a question from Alessandro.
Thank you very much for the very nice talk. I was trying to understand what is different between this and the kernel PCA. Would you agree that the difference is that you do not project everything in the feature space, but here you just the deflation. So what you actually remove is a nonlinear contribution, but the components remain in the linear space.
Correct.
Okay.
That's the difference. Yeah.
That's okay.
Yeah.
Okay. And then the other thing that I was thinking about was if you looked also into approaches such as nonlinear partially square, where or if you had, let's put it like this, if you had any problem where your state space or your x variables would be also related to would be the independent variables of some dependent variable. So if you have a relationship between your state space and some dependent variables.
So the assumption there is that was IID. The IID assumption was there. So if what you're saying was that non-IID, no,
yes.
we did not. Right?
Okay,
Yeah.
Okay, because in that case you would also like to describe this relationship between the two spaces, right? So
but you don't have this information available usually when you have data, right?
Yes.
So that's why you assume it's IID. Example.
Yeah, but for the PD it could be interesting because then in that case you might have...
I see what you're saying. Yeah.
You might have a source term in the PDE that is a function of the state.
Because so the problem there is that how do you encode the temporal coupling in this data? And you're correct. In that case, it wouldn't be IID, right? Because it's some kind of Markov structure.
Yeah.
Yes. Yeah.
Thank you. Anyway, it's exciting. Thanks.
Other questions? There is one on the back, and then okay, it's fine.
Oh, okay.
Please go for it.
Thanks. Thanks for interesting talk and for the interesting presentation. And I had a question concerning, that's more terminology one, but what did you mean by with, I think it was conditional entropy, am I correct?
Yes. Can we take it offline?
Oh, yeah, right. Yeah.
Yeah, it's right. The concept of entropy has to do with information theory. Basically relates to the informativeness of data, right? If you can predict the data, entropy is zero.
So it's like how much information
much uncertainty
remains useful.
Yeah, remains useful. Yeah. After you remove, yes, correct.
And analogous to in thermodynamics, how much energy can still use, except that here it's with information. So basically, what that is saying is that if the conditional entropy is zero, right, then the extracted data contains all the information. Everything else you can reconstruct from the extracted data, right? It's function of them. So in that sense, it contains no new information, right? If it's non-zero, then it means that you cannot reconstruct precisely the original data set from the extracted one, which means that you're leaving some information there. That's roughly at a high level what it means, right? And there's a mathematical, which you will learn in a couple of years.
So there was a question in the back.
Thank you so much for the talk. I don't know how stupid this question is going to be.
There are only stupid answers, no stupid questions.
Since you mentioned dynamical systems, I was very curious whether you could apply this to find projections in a simplex, for example, so that you can reduce your ODE to a specific subspace.
That's something that I would like to look at. Yes, absolutely. That's one of the directions we were discussing before, right? Right. And as it was correctly pointed out, right? Then how do you deal with the this is one shot, right? Well, how do you deal with the temporal dependencies, right? Because that provides some information, right? So I don't know. We're starting to formulate that problem, to be honest with you, and the application would be more to to PDEs. You know, in PDEs, there's, you know, Stephen Brunton, for instance, University of Washington, who applies this, you know, Koopman operators, right, to fluid dynamics, right? So I think that's the flavor of the work. We want to see whether we could use some of these techniques into that methodology. Right.
Okay, thanks.
Okay. Are there other questions? If not, or at least if you don't have questions that you want to make publicly, I want to thank once more Bruno for the nice talk.
Thank you.
And let's have a second coffee together, and then let's be back for the grand finale.
Finale.
Okay, so welcome back for the last talk of today. So the last talk of today will be given by Vincenzo De Florio. So Vincenzo De Florio got his PhD at KU Leuven in 2000, has worked in several capacity at KU Leuven and University of Antwerp, received the faculty award from IBM in 2013, and is very it was very active in fractal social organization. But today is going to present us something that I'm very curious about, that it's about generating music using dynamic systems. So I'm very, very curious. I will not go on, and I will give him immediately the stage so that he can show us and actually make us hear. I think it's more important what he does.
Thank you very much for this introduction, and thank you very much to Professor De Koning for inviting me here, and everybody here at BrIAS for this great opportunity. So, what is all about? As I already mentioned, this is an approach for composing music. So this is a talk which is extremely different from the most intimidating lectures that were preceding this one. It's not about science. The science part will be very much reduced. It's more art science, let's say, so very much different. Don't expect great mathematical models out of this. This will be rather elementary, let's say, from that point of view. So what we have here is an approach for generative music, which means algorithmic music. It's totally unrelated to AI. So the attribute generative might lead you to think of generative AI, but it's not. It's music based on for instance, a simulator of a system so based on an algorithm, let's say. So the structure is very simple. I will present my approach, and also I will demonstrate it with some music which I created with it. So the first thing is, dynamical systems. I'm a little bit sorry that we drop from high-level concepts to this level of elementary concepts. But dynamical system, you can see it as a function, a closed function in a set X, which takes, for instance, one input from this set and loops it around. And this kind of points that are like a trajectory in X, it's sometimes called an orbit. So if you take each of these points and you project it into a music space, you get music fragments that you can put together. And so this means that gives an idea why I chose the title of this presentation as Music of the Orbits, because actually it is a sonification of these dynamical system orbits. So an interesting thing for me was that this is fully deterministic, meaning that when you choose a certain function, when you choose the sonification function S also, and when you choose a point in the space of the domain and range of F, everything is decided. So basically, I will show that despite this determinism, I could create some music that, to my taste, let's say, has some interest and provided me with some surprise. Also, I will try to explain the lessons learned up to this point. So it all started with a dynamical system, which I dubbed Heartquake Dynamical System, which the model of which I published on Wolfram's paper, journal Complex System, some while ago. It is the model of a game called Beggar Thy Neighbor. In Italian, we call it strappacuore. It's played by two opponents with a pack of cards that they have to put on the table. This was taught to me by my wife, for which I'm very grateful. So it is actually I mean, it is not a game in the classical sense. It's more a pastime because it's a choice-free game. Again, like for dynamical systems, you take a pack of cards, you distribute it to the players, and that's it. The game the fates of the game are decided. Despite this, people played this game because the fates of the game fluctuate. It's very difficult to tell beforehand who's going to win. And if you play it very fast, it can be also, I mean, it can give you some heartquake, let's say, and that's why I call it like that. So you just move from one state to the other until you end and you have a winner. A basic question that I and my wife asked ourselves while playing this game was, yeah, okay, but is this configuration already known? Could it be that we ended up in a loop? And okay, I've take a look at the cited paper to have an answer to this kind of questions. But basically, what is a beggar thy neighbor? There is no time now to explain the rules and stuff. But you can think of it as a set of rules that change the ownership of cards between two players that have half a pack of cards each, and they are with the face value unknown, and they uncover one by one. And depending on the rules of the game, there is no time to delve into. The cards that accumulate, that stack onto the table, then can be won by one of the opponents. Okay, I took this, I generalized, I made a simulation, I wrote a program, I made a 3D representation, and blah, blah, blah. What is more important here is, if you have a look from this page of the paper, you have here a dynamical system, which it is the M, corresponds to the M in the previous slide. Okay, what you can do when you sonify is that you take the current situation as it is in the hands of the players and on the table. You translate it into integer numbers and then to notes, some way. So you have the original input, the f of the input, the f of the f, and so forth. And then maybe you add some simple rules to define rhythms, like if the note is repeated, note at step t-1 is equal to the one at t, then you don't play it again, like in ribattuto, but you prolong the duration. This introduces rhythm. And finally, there is an aspect which is taking these notes as they are generated in an abstract terms, assign them to instruments, and then finally hearing the results. Okay, if you take these three numbers, numbers like this is 6, 0, and 25, okay, you can consider them also as coordinates, and you can plot them. The interesting thing is that if you take packs, all the possible packs of cards, you divide them into chunks and you plot them, you get pictures like this ones that with a certain I mean, I didn't theoretically prove that there's a fractal dimension, but I fed them onto a program which told me that 99% it's fractal. It's a fractal dimension. You can see the self-similarity in such pictures. So you can expect maybe something from the sound of this type of system. Now, there's a property which I immediately realized, which is expressed with this strange sentence: genotypical expansion produces phenotypical expansion. What does it mean in practice? When you have pack of cards, and you have here 0, 0, 1, 2, 3, 4, 5, it's a pack of cards. And you have an extension to the pack of cards. So you add, for instance, 0 cards to to it. So there is a relation like the first is included in the other. Okay, this is like a gene which produces a body, which is the geometrical representation. And the geometrical representation has the same property. So as the gene is included, also the artifact, the body, is included. And something like this occurs also in music. So this is useful if you want to prolong the sound of something to intervene in the generation process. Okay, you can do also other things. I played a lot with this kind of things. One of the things that I did is if I have, instead of a pack of cards, a community of responders to a disaster, for instance, and you have I don't know, firefighters and so forth. You can use shapes to define the type of role, and then you can use colors, for instance, to say if the person is activated by the firing condition. There is a car, and this enables a role car driver to get into action. So I did something with the agent-based systems, all based on figures like this one, and I received from IBM a faculty award about this. Okay, this in a sense concludes the boring part. Let me just move to the music itself. So the classical question is, okay, but is it interesting? Yes or no? So I will start, I will let you decide, of course. So I will start with this, which is probably one of the first pieces that I wrote. I chose this one because it's nearly without intervention, purely generative. I mean, at the beginning of my series of experiments, I first gave the word to my simulator, and yeah, okay. Basically, I have here my series of numbers. I partitioned them into three columns representing substates of the system. And so I played a little bit, yeah, for instance, the first track, I only played the first column. It's like a restriction in the orbit. And I assigned them to bassoon and English horn. And then second piece, Kaidan, I did the same, but I added other instruments, and I played also the second column, and so forth. All right, let me see if this sounds plays or not. No, not this one. I want this one. Ah. Why doesn't start? No, doesn't want to start. Maybe I can do like this. Excuse me. If I play here. The graphical representation is I told you of two representations, the geometrical and the sound. This picture couples both. I use the POV ray light tracer to depict all the matches of this game, and then I moved the observer farther and farther away from a certain position in the scene, and I got this type of representation. Okay. I'll jump to some other parts of the piece because it's 7 minutes. the additional information is given by the second column. Okay. Right. I made a number of experiments. Some were really surprising, some less so. I had presented one. I had presented, for instance, I had prepared one in which, I improvise bass guitar on top of the generated music. But I think the quality of the broadcast system doesn't prevent me to... what I can do is show you this experiment. This is a classical movie, Dadaist movies, a movie of early 20th century. I took it, I reversed all the frames, and I used it as, I matched it to some generative music. And all the combination, all the results are purely incidental. So this is the original. In order to match audio and video, I had to speed up the original movie to 60 frames per second. So there's a number of synchronous moments between the video and the audio that were totally unexpected. Like, for instance, I will cut it short, of course. Like this one. And this was totally unexpected. Okay. And so forth. I have also other music, other experiments which I did, but I think I can cut it short and invite you maybe to have a look at my Bandcamp page where all these experiments are kind of collected. But yes, what I would like now to wrap up and tell you is that, okay, I made a number of experiments. The simplest things, and then I shuffled the input, I mutated the input, I made a random generation of seeds, I added special effects, I added guitar, bass, and so forth. One of the strange things, most unexpected things is this kind of conservation law, so that if you apply a little modification to the seeds, sometimes this leads to little modification of the output, and sometimes it does not. This is because of the rules of the game. If I change something crucial, that changes the fates of a phase of the game, then there will be a large modification. So in the end, I have something like a feedback loop. I select a point in a certain space, I sonify it, I assess the quality, and depending whether I'm happy or not, I apply changes, and I move on to a new x0 prime. Okay. sometimes there's this rule of little modifications in the gene produces little modification in the phenotype, and this can be used, can be perceived as adaptations in the durations, in the nodes, and so forth. So this gives a new meaning to the word composer. You compose, for instance, a selection of points and their orbits. So, as I mentioned, this is music from the orbits of dynamical systems. So the thing is, you have everything which is already decided from the moment you have F, the orbiting, the dynamical system, the sonification function, and also the seeds that you select. So you could say that these three elements represents a most compressed representation of the whole music. So if you would talk about entropy, as it was done in the previous talk, the zero entropy is given by this triplet. With that, you can completely reproduce the entire event. So everything springs out from that triplet. And I was very much surprised when I found out that Arnold Schoenberg, in 1950, came up with this idea of the Grundgestalt, which is the basic shape, the concept of the basic shape. It tells that in his model, which is actually a generative model of musical production, everything springs out from the team, can be traced back, so like it's the most compressed form, or put it still more severely, there is nothing but the team itself. It's like saying a human being, it's all contained in the primeval gene, in a sense, okay. There is much more to it, but in terms of information, let's say. Also, Deleuze wrote something that expresses similar concepts, and many others, like, for instance, Stockhausen with his mantra concept. It's nothing but an initial point that generates everything, like... now, of course, there is also Frank Zappa I'm a little bit addicted to, and he came up with this concept, maybe mutuated from other concepts, the concept of the big note, which says that the entire universe is just a vibration, and it all comes from a single concept. And we are the manifestation of that one seed, which is one note. You can find also in Leibniz, in Sikhism, it's not something new. We might have heard of that. So what next? I really would like, provided that BrIAS and Professor de Koning agree, to have an event like a concert for piano, bass, and laptop based on these concepts. And if you want to know more and to hear more, listen more to this kind of things, you can go and see and visit these things or contacting me. So many thanks. Would you have a question?
Don't know if there are questions or curiosities. Willem?
Thank you.
Yes.
Thank you.
Thanks. That was very enjoyable. So you mentioned you published the original analysis in Stephen Wolfram's journal. And so I remember Stephen Wolfram actually has made this efforts to define classification schemes for discrete
Yes.
time, discrete space, dynamical systems like yours. So you didn't really give us the details of the card game that it is all based on, but can you say something about like what kind of dynamics it shows? It sounds like there is some quasi periodicity in the output, and it goes on for a very long time.
Yeah, there is at some point some periodicity, because in the end you most of the time end in a cycle. So you have to focus on a part. I mean, if the simulator enters a loop, you have to break it. So. But indeed, the work of Wolfram was more systematic. He made a full analysis of all the possible evolutions of his game, let's say. And it would be interesting to sonify that, actually. So, but I don't know anything more than this. You can use this one and then...
That was great. I really enjoyed it. Did you look at dynamical systems which exhibit chaos and maybe compare different sonifications of very close initial conditions?
No. Very interesting question, yes. We did some experiments with other dynamical systems, for instance, based on chemical information, chemical systems organization. There's a colleague of mine in VUB that is kind of expert on this. So we did some, but they were still deterministic and non-chaotic. So it is certainly something to try. Maybe I should try it with nuclear systems, models of nuclear systems, and see if it explodes or not.
Thanks for a nice talk.
Thank you so much.
I'd be curious to hear about your subjective experiences regarding the control of the system. How much and in what ways can you sort of drive it to some direction you want, and how much do you play with the fact of being surprised by the outputs of the system?
Yeah. From a composer's point of view, I suppose you want to come up always with new things. And this contradicts, in a sense, the need for reapplying rules. But indeed, by playing with the system, for several years actually, I learned a number of rules that I could use to intervene heavily on the process. So from this very first experiment, which I showed you now, the first piece, I went to something that is, I call it hybrid generative, because there is a lot of intervention, a lot. Even the actual files that are produced, the final, let's say, I mean, there is a selection of the initial points, and a modification of the initial points. And you have a number of processes that I conduct at this level, at this stage. Then you get a final MIDI file, in fact. And then the game continued a little bit, and I started playing with the fragments of this MIDI file, modifying them. And so in the end, it is not more pure generative in my, let's say, production. Someone could do maybe a scientific, thoroughly scientific experiment, not intervening at all, trying to use only the machine, like in the first piece, let's say. Or even in that piece, I made some choices, like the columns that I selected. But it was very elementary. So it depends on what you want to do, if you want to go towards the science or towards the art. At some point, I was more inclined to go towards the art.
Okay, thanks.
You're very welcome.
Thank you very much for the fascinating talk.
Thank you.
I have maybe two questions. First of all, is the context of the research that you're leading with this? Like, how did it start, and in what context can you do this? Because I come from more designer artist background, and I didn't know you could do that at a nuclear. You're in the nuclear research center, right?
Yes, but I did not this in that. This was carried out when I was a theoretical computer science researcher at the University of Antwerp, and during my free time. I mean,
Okay. Yeah, that's
So
what I expected, but it's good.
I started playing with this when I was on camping with my wife and playing with my wife, and with on paper and pencil, I was starting writing the simulator or the properties of the system. Then went back and
yeah.
And the second question?
So the second question is actually going back to your last comment about like going more through art or science, and also the question of control. Of course, your system is really, you have really strict and strong boundaries in terms of the notes you're playing, the rigidity of the rhythm, and so on. And at last, you said that maybe someone could try to have no control at all on the system. And I was wondering what you thought about the new, actually, generative AI system that make music, which is more or less this, which is almost completely statistical, and the only control you have on them is the initial prompt.
I'm a little bit against the use of generative AI in music. I mean, I use glasses because they help me to see better, and this kind of system compensates for my lack of knowledge as a composer. Let's say it lets me do things, but still I want to be. I want still to do music for music's sake. I mean, I like that. So I don't want just a machine that creates something for me and it gives me the authorship of that without. What's the purpose of that? I'm not interested. Thank you. So, but with this, I could. Intervene more and more, let's say. And at that point, I felt that, okay, there were some musical opfers that were handed to me, but I would use them honestly, let's say. I could still say that I'm the author, let's say, of the composer better, in the sense that I mentioned.
Yes, okay, thank you very much.
You're welcome. Okay.
There was some. William, you had some questions. You want to go ahead, Bruno?
Fine. Did you do? I mean, maybe this has been done, and that confirms my ignorance. And
don't talk about ignorance, please. After your talk.
But did you try to do the opposite? Right, take a piece of music. And match it to...
Yes, it's very interesting because the concept of compression that I mentioned is exactly... Yeah, I thought about it. If I could take a piece of music and reconduct it to a finite set of functions and initial points, I would end up with a lossless compressor. Which would go exactly in the opposite direction. I thought about it, but I've not been able.
Yeah, but I mean, it doesn't have to match it completely. But maybe you can define a metric.
Then it's not lossless.
That's right. That's right. That's right. But it's still.
It's
okay,
exactly like you said that the entropy is zero, or we stop a little bit because for practical reason I don't. I mean, I can still use. I found. The most practical solution, right? I mean, number of iterations, for instance, as was you can go for the theoretical perfection, but maybe from a practical point of view, it's much handier to find the one that matches the problem at hand. So to have, for instance, a reduction of dimensions that is usable. Very cool.
Okay, so I'd like to thank once more the speaker.
Thank you very
much. And to invite my co-director Anne here at the podium so that we can we are really toward the end. Yes, I need the podium. No, okay. So, yep. We'll do it. Anne, your microphone. So, we are at the end of this season of this Brussels this is of the Brussels Institute for Advanced Studies. So all of this, it's the end of 2 years of work. The first year was last year, in 2024, where the theme was robotics as enabler or disabler for the Sustainable Development Goals, and this was led by myself and by my colleague Professor Bram van der Boer from the VUB, that actually wanted to be here, but he was stuck in a institutional duty. So he sends his apologies and his warmest regards. And so this was the beginning of this adventure with the BrIAS. So last year, it was not as easy as this year, I must say, because we started that this building was not ready yet. There was even uncertainty if it would have been ready for the end of the season. And so we were kind of the gypsies of BrIAS. So we had our guests in an apart hotel, and we were having the seminar every week in a different place, which was, let's say, quite interesting, because all of us have become experts on how to mount and unmount material and equipment, but extremely stressing. But everywhere, anyway, things went quite well. So we started from this idea of trying to approach how robotics could help the various sustainable development goals. And actually, we ended up with a program that was very interesting. So we had 15 BrIAS senior fellows, 2 resident artists, because we started this collaboration with whom I will speak about it more later on, and 7 junior fellows, and a lot of activities. So in the end, we organized more than 100 seminars. We organized 1 industrial forum and 4 public forums. It was a very, very enjoyable and fruitful year. And just to give some highlight, for instance, we had this forum on robotics for nuclear maintenance and decommissioning. It was in close collaboration with the industry. So we had several companies come and presenting what they were doing and interacting with the researchers. And we had every week seminars like today, but also some special events. And I'd wish to mention in particularly 2 that also show a little bit something about the philosophy that we used. So the first was on robotics in agriculture, was in February last year. And this was done in close collaboration with the previous directors of the Brussels Institute for Advanced Studies, because since the beginning, so Frank once told us, oh, by the way, if you didn't know, it's good that you know now, that once you are a BrIAS fellow, you're a BrIAS fellow forever. So it's too late. If you're already in this room and you're a BrIAS fellow, it's too late to go back. And then we thought, well, then if you are a BrIAS director once, you are it forever. So guys, from the previous program, you have to come here and work with us. And so it's the reason why we found this idea of working on agriculture. And this was a quite successful forum. And we also had a second forum, because then we started thinking we also have to approach difficult themes, not just easy themes where it's clear, okay, technology is the solution, great. But we also wanted to approach those themes where technology can be a problem. And so we spoke about the usage of robotics in time of war and in time of peace. And this was quite interesting because it's where we had people from very different backgrounds coming, from ethics, from law, engineers, people from the armed forces, people from very different experiences. And it was also a nice way to also involve other former directors of program of the BrIAS, because we had an historian from the previous program that also joined us and chaired the part of the event. By the way, if you have lost it, everything is on our website. Everything is now on YouTube. Go there. We want to become a stronghold of YouTube for cultural events in this area of the world. So go for it. So this was the first year. And the last part of the last event, finally, we were allowed to use this space. And we found out that, OK, this changes everything. It's much nicer in terms of dynamics among us, and it's much also easier to organize events. And so this year, we decided to go for a larger team, and I had really the pleasure that Anne come on board, and she brought her competence on AI. Me as also a control guy said, well, we can add a third word, let's add control to the team. And so we had this team on AI, robotics, and control with the same goals, sustainable development goals. And with that, we are at the season now. So we had 17 BrIAS fellows, 1 resident artist with home, 7 junior fellows, and we did quite a bit of things. Actually, who has been with us the last 2 weeks knows how intense were the last 2 weeks, because we had more days with events than days without. So we are going through some of them together.
Yeah, okay.
So I can skip this slide because most of you have seen it at least 3 or 4 times, so no need. So the first one, we continued with agriculture, because we said, again, that the previous directors could not rest, so they needed to work. And we went for this conference on smart agriculture. That was a huge success. We had more than 60 contributions, 70 people that were inscribed, that plus all the people of BrIAS arrived to more than 90 people present during the event. We had also another event in collaboration with Maitana Berechibar from the VUB, a colleague from VUB, on battery management systems. That was last week. Also, this was a huge success. We had more than 40 contributions, and at the end we were like 70 people around, always talking about the subject and working on it. So these were all 2 days events. And we also had a series of one-day events. I let Anne for some of them.
Thank you. So we'll maybe start with responsible AI, which was 1 day with, let's say, 3 main sessions where we looked at responsible AI from different aspects, I would say. So like interpretability, explainability, but also fairness was included, and then how this can generate trust, so that people would actually trust an AI system, but also trustworthiness, which means that a system is worthwhile to be trusted. So that's a difference. So trustworthiness and trust is not synonyms here. So we had 3 main sessions, I would say. So research was reported that is happening at VUB, at ULB. But then we also broadened the scope. So we also linked to TRAIL and FAIR, which are the 2 AI programs we have in Belgium. But also related this to policy. And of course, we concluded with a 4th session, which was a network session with many spotlight contributions. So BrIAS is also good at organizing networking with drinks, and that's very much appreciated. Also, the catering was always excellent. I think that can also be mentioned here. And then we had our second day on AI and law with 2 keynotes, but it actually went beyond, let's say, regulation. It also gave some light on how AI can actually also contribute to law, because law is actually a complex system. If you want to know more about this, and like it was already mentioned, everything is recorded, so you're invited to look at the recordings and enjoy again the talks we organized.
Then we can speak about the other two events. One was the event from on smart cities. It was an half-day event. It was extremely successful, and I must say, once that we have made work the former program directors, we decided we also had to make starting work the future program directors. So this forum on smart cities was organized mostly by Alessandro Parente, who will be director of program in 2 seasons. On the team, but he will say more about it, on the team of renewable energies. And there we had a very interesting discussion about smart cities, what it means, and actually it was very, very close also on one subject that it's the next subject, that is the one on democratic governance, because we spoke a lot about algocracy. So there were very interesting talks about algocracy and how AI might affect positively or negatively the way we organize our society. And the last forum that was last week on Monday was a forum on protection of critical underwater infrastructures. So it's a team linked to security and defense, and there we had several huge participation from the Belgian Navy, the Italian Navy, the European Commission, various agencies. We had a lot of very, very high-level talks, and at the moment it's a forum that continues to have echoes. I receive constantly requests for, can I have the slides, can I have some more information on what you guys have done, because seemingly it had a quite good impact. And also here, again, making work the next people, we had the pleasure to have one of the person involved in the next program, that was Jasper Van Aschke, who chaired one of the session, and somehow this is also one of the first point of contact between the former program and the next one. The season is not finished completely here, even if this is the closing event. So today it's the last day of a 3 days event in collaboration with Home, it's called Crossing Wires, concerning arts, AI, and robotics. We love having relationship with our friends artists. We have also, but this is already in the next program for in June, the first forum of the next program on democratic governance, and we will also have a concert later on in June. Now, before starting all the various thank you, I want to clearly say that again, everything is available on YouTube. If you're following, you know, from YouTube, you know that. If you're here, just keep following us. And since we have in the room the various representatives from the other programs beside us, I would like, first of all, to invite David to say a few words, since he was in the very first program of BrIAS, and was really, if for us was hard last year, for him was much worse because it was during COVID. So please, David.
Yeah, I just heard that you spoke about yourself like a gypsy of BrIAS. So when we started was just after COVID. So 2021, isn't it? The very first talk, we were like, shall we start or not? But now everybody booked the flights. We just booked all the apart hotel for all attendees. We sat down with the Frank and Serge and Christian, say, no, we must do that. We can now not call back, because we were just having like a second or third wave of COVID at that time. And we're like, no, we cannot call this one back. If we do this, we were afraid that it would never started. And so we had like this decision, okay, let's go and keep on doing. And so it was like, a very quite challenging program, but very much rewarding. So now I prepare a couple of slides, because there's one thing that I want to share with you on why we do this BrIAS. So And then I want to give you my personal why. So talking to people, getting out of the box, be uncomfortable, learn new things, not understanding 90% of what the people next to you is talking about. I think this is all BrIAS. But when you are inside these things, you don't understand that. You don't really grasp it because you are so busy in contacting people, in sending emails, damn, I have to solve this problem. Oh, coffee is missing. Shit, biscuits. Oh, yes, this guy needs this. Oh, yes, the pen drive doesn't work. I mean, you don't realize all this, and you might just miss the best part. So that's why you kind of have to let ferment. Now, our BrIAS was finished, and so in 2024, I could relax because I saw, okay, now all this dump of things is on these guys now. And I can sit in the room.
Support team.
Yes. I can sit in the room and then let's relax. In that room, I was in this first, let's say, what we call the first, but we know that was not the first agricultural conference that we were organizing. Let's say it was kind of a spin-off last year in Fari. And then I saw all these people presenting these drones that could fly over a field. Wow. Bringing sensors. Shit. Delivering molecule. Whoa. I'm producing molecules that can activate plants. These plants, once activated for the immunity, become more resistant to pathogens. They emit molecule by themselves as a signal. These guys are doing like sensors, drones, and so on. Let's talk to them. And then we're like, well, yes, let's apply for a project. Let's put together a project. Like that, we start to search. One call was out from the Circular Bioeconomy Europe, JU, Joint Undertaking, that was actually calling for more biological, sustainable plant protection systems with smart delivery. Fantastic. And then we're like, yes, we just have half of the team. We look back at the booklet, at the Facebook of the BrIAS, and we found many people there that could have been ready for the, let's say, for the challenge. And so people that we already knew, that we then involved more in the next season. So Paolo Falcone is here today. Then we have Maria Del Prado. Then she's a scientist at the CMAT today. She was BrIAS fellows are for forever. So we cannot say a former BrIAS fellows. It's a BrIAS fellows designing molecule that can activate plants. Then we got Paolo Maras making the drones flying. And of course also Zaifi Kadar. She's also working in one of these scale-up companies where they can produce more of these molecules. So all those were either BrIAS fellows, junior, senior, intervenee, just like coming and giving a speech, or be present to the Smart Agriculture Conference of the last year. We put them all together, and we got a project that is now starting. So yesterday was announced. So the grant was signed. We'll start the 1st of September. It's called Zelda, by the way. So we gave it this fancy name because, to bridge this, let's say, game looking like a philosophy of BrIAS. And so now we are ready for what will go good, what will be the best part of our job, creating new technology, bridging two different kind of worlds that could have very, very little chance to speak to each other. Biology and EI and let's say smart delivery and modeling and all these things I saw from your presentation all the time. So yeah, so this is the best part of BrIAS. Look next to you. You might have the next colleague that you might apply together for a project with, or write an article, or just have like an opinion paper. And so those are the best outputs that BrIAS can give you. If you do so, remember always to tell Frank to keep updated all the scientific output that we are producing, or you will produce. And so yes, so this is the BrIAS legacy. Not now immediate, but it might be just in future.
Okay, so then I would call next also Alessandro that will tell us about the program in 2 years, so that we can end with Emily with the next program so that she can really promote it in the right way.
Thank you, Emanuele. So I didn't prepare anything. But anyways, yeah, in 2 years we will start a program that is and we will be actually 4 professors from ULB and 4 from VUB, and it's actually oriented towards sustainable transformations in the perspective of a just transition. And so we will tackle not only the problems of decarbonization, but also all the aspects related to social implications, interaction with civil society. And the nice thing is that we already have a multidisciplinary team. So I'm a pure engineer, I'm simple engineer, but we will have in the team people from economics. So Marek Udon from ULB, Tom Boiler from as well ULB, and Wouter Achten, who is an expert in life cycle assessment. From the VUB side, there will be Kati Makaris. She's also very well known in this field of sustainable transformations. Bas Van Eur, who is here in this building, in Cosmopolis Group. Davis Bastens and Aurélie Bellons. So it's a multidisciplinary team already that really promises a multidisciplinary and holistic view on this very complex topic. So we really look forward to that, and we will also rely on the help of the previous directors, no?
With pleasure.
With pleasure. And now Emily will be one of the 2 directors for the next season. You sure? I mean, please go.
So, thanks a lot. Thanks a lot. I'm very happy to announce this new BrIAS program on democratic governance, challenges, and innovations. We innovated with 3 N's. That's already that's mainstreaming innovations right there. So together with Sylvia Herzl, who is a VUB colleague, we are very pleased to be the next program directors for the next 2 years or more, as I understood. So to say that democracy is under pressure today is, I think, an understatement. So in times like these, we thought independent research into the challenges, but also the remedies or innovations for the future of democracy is really vital. So we aim with this program to explore not only what's going wrong, but also, because I'm a hopeless optimist, how we can renew and reinvent democracy for the future. So for the next 2 years, we have plenty of activities, and we really hope to contribute meaningfully to this effort, of course, with the BrIAS community, so you're all most warmly welcome. We will start on June 5th with our first forum. It's a public forum with the idea to mix academics, but also members of civil society. So we took also, I think we had the same inspiration with the sustainable goals, but the program that we aim to put together explores these four critical challenges. The first one is the first work package is polarization. Polarization, populism, divisions, and violence. Because the question of how political and social divisions between groups challenge democracies today, I think is crucial to understand, and challenge also democratic norms of pluralism and tolerance. So that's a big pillar that we want to investigate further. The second one, and I think there's great connections also with the next year's program, is democratic short-termism and sustainability, where we will investigate the question of how we can better equip democracies to handle long-term challenges. Climate change, budget deficits, social sustainability, etc. Democracies and are democracies compatible with long-term decision-making? That's really the core of this pillar. Then work package 3 connects to the former program with technology, misinformation, and AI, where we will investigate a question how digital technologies and social media have reshaped democratic processes, how democracies can counter the spread of misinformation, manipulation of public opinion, the role of AI in preserving open debate. So this is, again, a third pillar, and I really see the connections with the past and future programs. Fourth pillar is diversity, inequality, and inclusion. We will consider how democracies can address inequality in terms of wealth, income, economic power, but also structural inequalities linked to gender, race, ethnicity, social class, etc. And that will, again, be the focus of this work package. Then we have a cross-cutting theme, because we are hopeless optimists. We have the theme of democratic innovation, to see how democracies can be redesigned, innovate to tackle these challenges. Another transversal theme is the interaction between art and democracy, and art can be mobilized also to renew democracy, basically. And also the roles of cities there. So art, cities, and democracy is also a cross-cutting theme. So for that, we have a very interdisciplinary team that we put together. So each work package is led by a VUB and ULB colleague from different disciplines. So you see the first work package is Jasper Van Asch, and he already participated to an event previously, and Bram Spreut from VUB. The work package 2 on sustainability, it's Louise Knops, and you see their connections with the next work package. She's a colleague of Tom Bowler at ULB, and then Didier Caluarts at VUB. Work package 3 is Caroline Close at ULB and Ike Picone at VUB. Work package 4 is Daniel Zamora at ULB and Karen Celis at VUB. So it's very interdisciplinary with scholars from political science, sociology, communication, architecture, psychology, etc., and computer science. And we hope to also bring in more people from science. So I'm really happy to advertise the new program here today. Activities, we will run a lot of activities. I'm not going to bore you with that, but there's going to be visiting fellows, of course, seminars, of course, summer schools, big lectures, public forums, international conferences, but again, a lot of connections with art and architecture, because I really think this is the distinct feature of this type of program. And that's not for today. But so, yeah, first event is next week, next Thursday, June 5th. And we have a public forum where we will ask members of the academic community and members of the civil society to identify key challenges, because we also want to have some input from these actors to feed our program for the next 2 years, to also organize events that are meaningful for people and people want to attend. And so by having this first forum where we will discuss which challenges democracies face in practice, will help us identify themes for activities in the next 2 years. So if you want to contribute, you're most welcome next Thursday for the whole day, part of the day, whatever fits your schedule. Thanks a lot. Looking forward.
Thank you. Okay. Okay, so we are really toward the end now. So I would invite one of the two director of the BrIAS, that is Frank de Koning, to come here in such a way that he can distribute, as we will call them, the certificates to the various fellows. In the while, I will find my. Okay, we can. Well, we have a list. We have a list. We have to list. We want to list also the people that are not present because I think it's nice. But we can start with the first one.
Yeah. So first we want to call Rafael Velio Perez to receive the certificate. So.
Thank you. And can someone make some photo, please? Yep.
Should we join? Welcome to the other side. Yeah.
So Rafael from Cuba was really a nice presence in our
trustworthiness workshop, very prominent.
Absolutely. Yeah. And the second I would like to call it's Yael Edan. So Yael is actually the only fellow that was in both the 2 years because for various technical reasons that was the way we had to do it. She was really, really important in all our conferences on agriculture and not only. So I think you gave 5 seminars in these 2 years, and every time on very, very interesting subjects. So thank you for being with us.
Next is Paolo Falcone.
So Paolo, as you have seen already, his photo in the slides of David. Is one of those crazy guys from robotics moving to agriculture. So Antonella is not here with us because she was here in February and she already received her certificate back then.
Next we have Ilya Kolmanovsky. If I pronounce it correctly, sorry.
Ilya is, well, I've presented him before, so I avoid presenting him again. Let's have a photo.
Add it was an extremely accessible talk you gave earlier today. So thanks for this.
So the next was Luca Magri, that is not here with us because he was at the beginning of the program. He already received his certificate.
Yingling Mo is unfortunately also not here, right?
Yep.
Yeah.
And also Zhang Yan and the next one, Marco Marco Mikotra, thinking to someone else. And the same Alessandra Parisio and Andrea Roli, and also the next one. I'm doing like this, sorry. Yeah. And the Yuki Sawada also, they are all people that were in the first part of the program. They all received their certificate at the time.
Next we have Bruno Spinopoli, sorry.
Sinopoli.
Sinopoli.
So Panagiotis Simonidis also, he was previously, so he's not here with us. And the next one,
Hannu Toivonen, yeah,
he is definitely here.
Who also gave several talks and inspired us a lot with combination of AI and creativity, different points of view. Thank you for this. And then also Willem Zadema, who also gave several talks, more technical, more inspiring, related to art, the whole...
And let's not forget the hackathon that we organized. And then next one is a very special person because he's our resident artist. So please, Guillaume Zlizevic.
And I think now, oh yeah, sorry. Too early, too quick. Sorry. And now we move to the junior fellows, right? So next I want to invite Merdat Asadi. So they did a great job in all kinds of supporting roles. Thank you very much.
And the next one is Elias Fernandez Domingo.
Also, thank you very much for supporting the event. Yailen Martinez. Also very active in the series of BrIAS events.
So the next one is Luca Rossini. He is the only junior fellows that was in both seasons and that worked like crazy. So I'm really grateful to him. And then some other special people that are the thematic program chairs, so the people that have helped on specific teams. And the first is David Canella. That, yeah.
Yes, that's something we still have to explain. Yeah.
So David was, as said, this year I involved him very, very heavily because I said, you are a former director, you have to work. And we organized this huge conference. He also gave a talk. He was present a lot of times, very often saying, oh, I'm not really understanding, but it's fine.
Thank you so much.
For the not understanding, I imagine.
Yes. For all the uncomfort zone that you gave me. Thank you for this very nice thing about.
We will explain later.
Alessandro, same thing. He organized basically alone an important event. He invited one of the fellows. He was very, very active. So.
Wow. That's a nice one. My first one.
Dimitris Sakaridis, who's not there, I think, but was very, very active.
And same applies for Leander Schietgat, who was also active in organizing, amongst other, the Trustworthy AI event. So we will, I guess, hand over the certificate
to them,
later on.
Yep.
Yeah. And of course, I want to thank my co-director here, Emanuele Garrone.
Thank you. And my co-director, Noé.
So we can, thank you. Can be together on the picture.
And there is one missing. There is one missing. And is missing the chair of everything. We have the chair of everything missing, Anya. Yeah. Who was worked like crazy on Thursday and Friday. Yes, it's here. Yay!
It would be the second time with Emanuele.
Alejandro is one of our junior fellows who really did a lot, especially for the latest conference on battery. And moreover, I must say personally, he managed a lot of things in the department I could not manage because I was here. So I'm really grateful also personally to him.
I think we should also say something about the certificates.
Please, I have a conflict of interest.
You have a conflict of interest? No, I don't think so. I don't think you helped any with this anyway at all. No, it's all handmade by Anya. It's amazing. Yeah. So we all have a unique piece here. So it's really personalized. So thank you very much. This has must have taken a lot of time. I know you practice, I don't know how to say this in English,
calligraphy.
But still, I think this is a lot of practice, so you're really an expert in this. So thank you very much for this nice certificate. It's a unique piece. Thank you very much.
So I have to thank Anya too, also because otherwise tonight she will not let me back home. Because as you all know, she doubles in the role also of being my wife. Poor thing. And I also would like to thank the various other people that have helped in this season. So first of all, the two directors, Frank de Koning and Serge Aumont, that are really... So it's rare to find people that you go to them with a crazy idea and they say, yes, but let's do a little bit more than that. So it's very rare, it's fantastic. And also there are several people that have worked a lot behind the scene. In particular, there is Valeria, who worked a lot behind the scene. Sophie, Liliana, and Anastasia, who worked also quite a lot behind the scene. Probably they are even now behind the scene. Then a special thanks to Andres, who last year was a junior fellow. This year he was anyway here helping. So if you see the beautiful graphics of all the various events, of all the various things, it's all his work. He was the one who set all the graphics and who set the very high standard for the audiovisual. So he did really an amazing job. And with this, I imagine that you are all tired of me saying blah, blah, blah. Guys, no, okay.
Let me say a few words, because Anne thanked Emmanuel thanked Anne, but let me thank you both, and not only you. And when I say this, it's also on behalf of Serge Aumont, the co-director from ULB, who unfortunately could not be here because he is not in Belgium. Let me thank also, it was said, the staff, the actual staff, but also the previous staff on which I would say we have built BrIAS. Annette Hansen and Silvana Porky were the predecessors of Anya. You had Fritz Heinrich, Christian Hermans, Bram, you mentioned, etc. So it's thanks to the contributions and work of all those people that we were able to, I would say, go to the rectors and vice rectors and say, look, BrIAS is really a success. But we have to be fair, we didn't do the work, you did. And the fellows did, and the junior fellows did. So really our most sincere thanks to all of you for the fact that from now on, I would say as directors, we can mostly rest, okay?
And now, let's go our well-deserved drink. Thank you to everybody.